Um, Hi, I'm Anna. Me and my fellow organizers, we have Lee over here and Andrew. And now I'm not on again, okay. We're very, very excited to welcome you to PLMW. We have a really exciting program today with some great speakers and panelists. And we also have a fun event this evening at Jane Street's offices that's going to involve dinner and board games. So we're excited to see you literally all day. For our first speaker, I want to introduce Derek Dreyer, who is faculty at Max Planck, and he's going to be here starting off the day because he's program chair of POPL'. So, Derek, take it away.
All right. My slides are not showing, so let's let's hope this is working better than yesterday. Yes. Good. Great. Okay. Hi, everyone. Can you hear me in the back? Great. Thanks to Anna, Leo, and Andrew for inviting me and for organizing this workshop. I've been involved with PLMW for many years, both organizing and giving talks, and it's a lot of work organizing these workshops. So if we could all start with a little round of applause for the organizers, that'd be great. I'm talking to you today. I'm going to give a sort of brief talk to open this workshop. This is sort of traditionally a talk that the program chair of the conference gives to sort of give you an idea of what it's like to attend a conference. Out of curiosity, how many of you have attended POPL' before? Okay. How many of you have attended any conference before? Well, a few more. Okay. And how many have attended no conference? All right, most of you. That's great. Okay. I'm going to give sort of some words of wisdom based on my experience over the years, starting from when I was, the first POPL' I attended in 2000, and some things I've learned that I think can help you have a more enjoyable and fruitful experience here. So the first question is, what are you trying to get out of coming to POPL' or any conference? I think there's basically two main things. Oh, and by the way, before I go on, I should say a lot of these slides are based very closely on slides that Amal Ahmed used last year when she was program chair. So I should give her credit for that up front. So there's two basic things you want to get out of the conference. One is to get a sense of what research is like in the field. And the other one is sort of social networking, trying to get to know people, particularly people in your cohort, but also senior people as well. So let me talk about these two. I'm basically going to talk about these two things. So in terms of what is, what to get out of the research or what to learn about the research in the field, this is, let's look at the POPL' program here. So this is basically what's going to happen over the next 3 days. There's going to be two invited talks on Wednesday and Friday morning from Azadeh Farzan and Nate Foster. There will be 93 papers, which is a record number of papers accepted to POPL', selected from 319 submissions, which is a record number of submissions to POPL' this year. So the field is pretty vibrant and healthy. And that's presented in two parallel tracks over the 3 days. 9 of those papers received Distinguished Paper Awards, so those are papers you might particularly look out for. The program committee felt they were particularly strong. There's a business meeting. I might say, why do the students care about the business meeting? I always found the business meeting fascinating because this is where you sort of see a little bit of how the sausage is made. Also, I'm speaking at the business meeting, so you should definitely you should come to the business meeting. No, but it's not just boring business. There'll be a report from me as the PC chair. There'll be a report from Philippa Gardner as the general chair of the conference, and a bunch of awards are given out. I think it's always a very interesting meeting. There's receptions on Wednesday and Thursday after the conference at something like 6:15, 6:30. I highly recommend you go to those. Those are really good networking opportunities. There are session previews. So this is, I'm going to say more about session previews in a minute, actually. So I'll leave it for the next slide. And don't forget the POPL' song. So this is not exactly a tradition. Sometimes we have a POPL' song, sometimes we don't. But this time, Ali Donaldson and John Wickerson have prepared a special duet for Friday morning right before the keynote. So I have not heard this, but judging based on past performance, you should be there. Okay, so highlighted in red are the things that I would say are like musts. You should really definitely do all these things. So of course, I'm leaving out like most of the conference here, which is the 93 papers and the session previews. So let's talk about that. So I think my first message about attending a conference is don't let the conference, in particular POPL, happen to you, okay? You should happen to POPL, right? So a common failure mode is that you come to the conference and you're kind of passive and say, oh, there's all this exciting research. Oh, I don't know anything about it. I should just sit and attend all the talks and try to soak up everything. Don't do this, right? You will get completely exhausted. You'll tune out. I know, having been a student who did this, right? It's just you get a little depressed. You're like, oh, there's all these great people. They're doing all this fantastic research. I can't understand any of it. Well, guess what? I come to a conference, I go to some talks, I can't understand them either, all right? So, and I've been doing this for, I don't know, 25 years or something. So it's, that's completely normal to not be able to follow everything. And if you just try to follow everything, you're gonna get really burned out. So what I recommend is the following. You can do some variation on this, but basically look over the program up front and see if there's a few sessions, maybe 4, and this is a random number, but something like that, that you're really interested in, like that seem like an area you're particularly interested. Go to those. Then look for some others that you seem maybe could be interesting, but you don't know that much about the area, all right? And for those, I would say check out the session previews, which I'm going to say a bit about in a second. But the session previews will give you sort of an idea of what that session might be about, and then from those you can choose a couple sessions you want to go to. And if you miss a session, say you're talking to someone and you miss this session you really wanted to go to, don't panic. Everything is being recorded. Everything's being live streamed to YouTube. You can watch talks later. You can watch it from your hotel room. Like there's no disaster if you miss a talk. So it's more important actually that you engage in the conference in an active way than that you just sit in talks. So these session previews I want to say a little bit about. This is something we just started last year. This is, and this is current, this year it's being organized by Nate Foster and Clément Pitt-Claudel. I think this is a really nice service. So these are basically 10-minute invited talks, one for each session of the conference. And the idea behind this is that these are talks that you would see before the session. In many cases, they're right I think on the Thursday, they're right before the session, and on Wednesday and Friday, they're like an hour or two before the session. They're intended to sort of make the session, or make POPL in general more accessible and give you some idea of what the papers in that session are about, and maybe a little background on the topic. So I highly recommend you go to some of these, specifically for the things where you're not completely sure about the area, but you're sort of curious. But don't go to all of them, all right? This is a really nice service that people are giving these talks, and I'm amazed that we got so many of these session previews organized in the last month. But if you go to all of them, you're not gonna have any breaks, because these are during the breaks. So be judicious in attending these. And sort of my general message, as I said before, is like, don't worry if you don't understand everything you see, all right? Be happy if you understand something and you want to learn more from that, okay? I'm always happy if I go to a conference and I come away having learned something. Okay, so that's sort of getting a sense of PL research. And then the other key aspect is the sort of social networking part. So there's kind of two groups of people you want to really network with. One is other students. So I think POPL and PLMW especially are great opportunities to meet other students and befriend other students, particularly those in your cohort. Like if you're about to enter graduate school or apply for graduate school, or you're an early graduate student, there's a lot of students here in that same group. And often I know a lot of people who met other students at this kind of event, and then they remain friends for many years. And that helps when you go to other conferences. Then you have a sort of starting point for networking with other people. And a key thing here is just if you came with, you might have come with one other person, say, who you know. Don't just hang out with the people who you came with, the people you already know, right? Try to meet new people, because otherwise you'll sort of, this is another classic failure mode, is sort of hiding in the corner with the other student you know. I know, because I did that. It doesn't work. So try to meet new people. And when you meet other students, ask them about their experiences. Like, this is a great opportunity to learn about people around the world who are trying to study or trying to get into PL. people in different universities. Very different universities have very different styles of sort of how they work and what research is like there, what it's like to work with different professors. Maybe you're applying to grad school and you want to know, what is it like to work with Professor X? So go talk to their students. There's a decent chance that some of them are here and they might be willing to tell you what it's like to work in their group. Of course, sharing wisdom about applying for grad school. So the other group of people you want to talk to or you want to get to know are sort of more senior people. And this is always difficult because they're very intimidating. I'm a senior person and I'm intimidated by them. Many of us are not naturally extroverted, or we may be some mixture of extroverted and introverted. And when it comes to social networking, I tend to be a little introverted. But you have to try. So I recommend trying to approach faculty or senior people during breaks. That's a time when it's often easier to approach them. They're a little scary, but they're mostly normal people, mostly. They want to talk to students. Faculty love talking to students. If you're seated with them at lunch, for example, there are these big round tables at lunch. Go sit at a random table, or maybe pick a table where there's someone you want to talk to, and don't be shy. Just introduce yourself, even though it is awkward. It's always awkward, right? Everything's awkward about introducing yourself to people you don't know. I know that when I sit at a table with a bunch of students, I also feel awkward. Right? So if you introduce yourself to me, it makes me feel much more relaxed and more willing to sort of, start a conversation. And ask about their research, right? People love to talk about their research. They love to give advice. Most of them, again, there's some who aren't interested in talking. There's some who are very introverted. Don't take that personally. It's not like they're annoyed at you. That's how they are. Talk to someone else instead. Most people really love to share their wisdom, and they love to give advice. And sort of just to sort of moving towards my conclusion here, the key thing is try to be intentional. As I said, don't let POPL happen to you. You should be thinking about what you want to get out of POPL. Be proactive. One way of doing this is look at the program, or maybe you already know about some people's research who you're interested in. Pick at least 3 people who you want to talk to during the conference, more senior people. You could also be senior grad students or someone whose research you're interested in, and go seek them out early, not on Friday. Right? Seek them out tomorrow. And try to nail them down for a specific time to chat. Or maybe they'll be willing to chat right that moment, but often you come up to someone and say, oh, I have this question about something, and they say, oh yeah, that's great, I can't talk right now. Ask them when they can talk, and follow up with an email, and try to get them to actually settle down to a particular spot. It doesn't have to be a long slot, maybe it's 15 minutes, maybe it's half an hour, but try to be proactive about getting them to talk to you. And then it's helpful if you really want to get them to talk to you, it helps if you have specific questions. So if you just go up to some senior person and say, I'd like to talk about, I don't know, research or something, or what it's like to be a researcher, they'll say yes. That will be something where they'll think, well, maybe I could talk to this person for 5 minutes. But if you have a specific interest in their research and you say, oh, this paper was really interesting, I had a question about such and such, then they might say, oh, well, actually, that sounds like it's more worth my time to talk to this person. So try to be more specific in the kind of questions you ask. And lastly, don't forget to have fun and get some rest. So being at a conference is really exciting, but it's also, I find, very stressful and a little tiring, actually very tiring, especially by the end of the week. So take some time off, not a huge amount, but make sure to take some time off to enjoy being in London. We're in a great neighborhood around here with museums and great restaurants and shopping, et cetera, and theater. Do something to enjoy the location, and maybe even take a nap. So with that, I thank you for your attention, and I hope you have a great POPL and PLMW.
I think we have time for a question or two if someone has one.
Hi, Derek. I'm a COVID baby. So this is actually I'm quite well into my PhD, but
Right.
This is only my second conference. Is there anything specific? I'm thinking about maybe postdocs, etc. is there any specific advice, or is it just more of the same?
That's a good question. I haven't thought specifically about that, but I think it's mostly the same. I mean, you probably do know some more people, at least you've communicated with some other people in the field, even if not in person before. So, and you probably have some idea of who you might want to do a postdoc with. That'd be natural people to talk to, of course. Yeah, I mean, I know COVID was very rough. I also had several students who had several papers published before they could actually see get to a real conference.
Thank you.
Then I'll ask one more question just to close off this mini session. Derek, could you quickly talk about an interaction you had at POPL or another PL conference that you thought ended up being really important in your later career? Like someone you met or
my later
interacted
career or anything?
At
Okay,
that time,
well,
yeah, something that stuck with you.
Yeah, these questions are always really hard.
Sorry.
You could have told me that in advance. Anyway, okay. No, I can think of one just off the top of my head. Was actually one of the first conferences I went to as a postdoc. It was ICFP 2005, and that was where I think it was Manuel Chakravarty and Gabby Keller had a paper with Simon Peyton-Jones on associated type synonyms in Haskell. The details are not important here, but I looked at the paper. I thought this is really neat, and this looks like to me an application. This is sort of an instance of the kind of things we do with ML modules. Anyway, I went and talked to them at the conference, and they were super friendly. I mean, I had known them before. They had visited CMU at some point, and so I had met them then. But they were super friendly, and we just started talking. And that was actually the first. I ended up visiting them in Australia afterwards, and that was the first. That was one of my first papers that I wrote after my PhD, and that was really sparked by. Networking with people at a conference based on just seeing their talk and thinking this was related to my work. So again, I was proud of myself for being proactive.
That's perfect. All right, let's thank Derek again.
I'm wrapped up here. Hold on.
So while Derek unwraps from the mic, we're going to do a little social icebreaker activity next to get you all kind of up and moving and talking to each other, as Derek suggested. So we've made a little PLMW bingo card that I'm going to put up. And then you will have to get up and talk to people. It'll be great. The resident extroverts will help. Thank you, Derek. It's like, how many PhDs does it take? We show you PLMW bingo. Okay, so here's a little bingo card that has a bunch of random things like, let's see, who's been in a helicopter? I have not, sorry. So I'm going to have you get up, walk around, and see if you can find people who have done these things. You feel free to keep track which ones you've gotten, and there may be a prize for the person who's got the most. I'll help start you off. I don't drink coffee, which apparently makes me unique among computer science people. But once you meet me, you'll realize that's probably a good thing, that I don't drink coffee. You can ask Leo and Andrew over there for confirmation. All right, up we go. You all were so good at that. Well done. Well done. We were like, oh, are we going to have to walk around and like make sure they're actually mingling? No, I didn't have to do anything. You guys were great. Hopefully you found that fun. So next, I would like to introduce Nick Wu to come up. And Nick is at Imperial, and he's going to tell us things about effects. And it's going to be great.
Okay, good, great. Okay, well, thanks for the invitation to talk about this stuff. And it's great to see so many of you here. So well done for making it, and well done for being so brave to talk to one another. That's something that I don't think I would be able to do. Today's talk is about the evolution of effects. And my goal here is to give you a talk that's not actually technical, it's actually more historical. And what I'm trying to highlight throughout this talk is the degree to which innovation happens in lots of small steps over a very long period of time. And hopefully you will all become part of that tiny evolution of what humans get to know. Okay, so the story is about effects, and it's basically a brief history, and it starts with programming language in the large, moves on to something called monads. I'm curious, who knows what a monad is? Great. And then we talk about these things called effect handlers, and then I'll be talking about higher order effects, which is the stuff that I've been working on. And so the caveat is that there's just too much to history for me to even nearly cover everything, and I will make mistakes, and I will make omissions, and so this is just difficult. Right, so the story starts with functional versus imperative programming, and functional programming inhabited by Alonzo Church in the early days, and his PhD student, Alan Turing. And it's really fun because, of course, Alonzo Church says, the way to do computation is to use the lambda calculus, and Turing says, no, we want to be using assignment statements instead. And so right from the beginning of computer science, really, we see this tension between the two. And so my research has been trying to resolve this tension. So I laugh because I'm the head of the functional programming group, except all we end up doing is imperative programming all of the time because we're just trying to deal with effects. So there's that. So I'm going to just start with a brief history of programming languages. And because we're in London, let me take you back to London in 1666. And London is burning. So there was this fire that started off in some bakery, and much of London got destroyed. And people drew beautiful pictures of the event. What also happened in 1666 is this man called Leibniz finished his PhD thesis. And his PhD thesis was the art of combinations, or combinatoria. And what did he do in that work? Well, he extended, he basically talked about a proof of the existence of God from various axioms. And he decided that what was important was to have a kind of an alphabet of all human thought so that he could combine the ideas so that you could talk about ideas and combine them into larger ideas and argue about them formally and semantically. So that was an important piece of work. Because again, we're in London, one of the ideas that he had was he said when he was trying to get from England to Holland, he was detained for some time in the Thames by adverse winds, can you imagine? During that time, knowing not what to do and having nobody in the ship except sailors, I meditated on things and especially thought about my old design of a rational language. See, he's a PL person from the beginning. And for if we had such as I imagine, we could reason about metaphysics and morality just like we do about geometry and analysis. And that was a letter from him to Galois, a different Galois, in 1677. Okay, so he was a programming language designer. A little bit later on at a conference, there's a keynote where this guy, Dubois-Reymond, says, ignoramus et ignoramibus. We do not know and we shall not know. So he's talking about the sum of human knowledge and how there's just too much to know in the first place, and actually certain things that we just won't be able to. Well, slightly later on, Hilbert, at the same conference, also gives a keynote, and I think gives a response to what was said before. And he says, wir müssen wissen, wir werden wissen. We must know, we shall know, in defiance. Well, Is that how things turned out? In 1928, Hilbert and Ackermann formalized the decision problem, the idea that given an input and a first-order predicate statement, was there a way of always determining whether there was an answer yes or no to that particular problem? We shall know was the thing that he wanted to know. But in 31, Gödel, of course, gave us the incompleteness theorem, and that told us that actually there was no system of logic that could be proven to be complete in this sense. But maybe there'd be some way of having an algorithmic system that would be able to break that. Maybe algorithms were the solution. And of course, we get two independent results by our friends Turing and Church saying actually no such algorithmic procedure is possible. And they do that from very different perspectives, one by building the Turing machine and running some tapes through, and the other one by proving limitations of what can be expressed mathematically in the lambda calculus. OK, so Turing machines were in the air, the war breaks out, and von Neumann was a really big name at the time. Von Neumann was in charge of basically building a computer, and so started the so-called von Neumann architecture, which is very much what our computers are based on now. So you've got a store, and you've got registers, and instructions that pass through these things. And so he was very much in charge of the EDVAC in 1949. History of computing, or computers, sorry, is actually very complicated to get right. There was also the EDSAC, which was the British version, made in 1948, slightly earlier than the Americans. But actually, there's lots of controversy about what came first and which is the right machine. And then there are even earlier machines in this, and what is a computer, and blah, 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 blah. So I'm not going to go into any of that, right? But the point is that these machines became the beginnings of programming itself. So rather than having lots of instructions, Backus basically said, I'm tired of writing in assembly. I think I would like to write things in a higher order language, in a human language. And so he says, much of my work has come from being lazy. I didn't like writing programs. And so while I was working on the IBM 701, basically he made up a programming language. And so he says that most people think that the main contribution of Fortran was to be able to write algorithms in terms of formulae. But actually, for him, it was the organization of loops. So I think this is an interesting point because we often think of programming as making specific statements, but actually programming is very much about control flow and trying to organize that, which I think is quite an insightful thing that he's saying here, because actually when we get into the idea of effects, the hard part is not so much all the algebraic evaluation. It's not the part that's sort of mathematical. It's the control flow that's the difficult thing. So this is exactly where I'm in agreement. OK. At around about the same time, or very little bit later, you've got this programming language called Lisp. I'm curious, who knows of Lisp at least? OK, I think most people good. OK, that's good. They still teach things in school. So Lisp is a very early language. Basically, the idea was that it was an implementation, in some sense, of the lambda calculus. And he introduced things like the conditionals. So when you use an if-then-else statement, that was originated by McCarthy. That you should not call them if-then-else statements. You should call them McCarthy conditionals. And he introduced recursive functions, at least recursive functions mechanically in this language, and Lisp processing. But rather than having head and tail, he called them car and cudder, right? And higher order functions were there. So we can see conditionals being expressed here in his paper. Where he's saying it's a good idea to have pattern matching and to cover your cases. And bear in mind, this is in 1960. He also has this function here. I'm sorry it's so small, but it says map list xf equals if it's null, then do nothing. Otherwise, if it's this thing, do. So this is exactly the mapping function that you would find in Haskell. And the car and cudder thing is quite funny because that has more to do with the registers in the IBM machine where you would find the head and the tail of the list. So we're talking about lists in terms of pointers here. And he also coined the word abstract syntax in '62. So I think a lot of what we're going to see in this talk is it feels like everything was invented in the 60s and 70s. But my point is it wasn't invented in the 60s and 70s. They had a green field to start with, and they came up with lots of the original concepts, which we've been refining ever since. And so your job is not to come up with new concepts from the ground up like they did, because they had it easy. Your ideas will be to just improve things incrementally towards something better, right? That's the goal. OK. You might get lucky, but OK. So in '58, these two characters, Backus and McCarthy, amongst a whole bunch of other people, like Peter Noir, invent this programming language called Algol. Now, Algol is probably the first proper programming language after the previous two, but it was actually a very special language because it looks very much like imperative programs today. And Tony Hall remarked that it was a language so far ahead of its time that it was not only an improvement on its predecessors, but on also nearly all its successors. And so there's some truth to that in the way this language was. There was iteration and recursion. There was a distinct assignment versus equality. Code blocks and lexical scope came into this. We had nested procedures, procedure passing, BNF, call by value and call by name. All of these things came with Algol. I mean, it's phenomenal that they had so many ideas in one go. I didn't put the slide to it, but there's a funny picture of the way this of the committee that designed this language, where they're all putting their hand up. It's a nice black and white photo where you can see the group, and apparently that is the only time when the entire group agreed on anything at all. And the question that was asked to them when they all put their hands up was, do you agree to have your photograph taken? All right. In '64, we get this, this chap called Peter Landin. So Peter Landin wasn't part of the Algol committee, but he made some really huge contributions towards its development nonetheless. So one of the things that he did was he wanted to think about how you could mechanically evaluate expressions. So by expressions, we're talking about what he called applicative expressions, and they are, they almost look like Haskell, where you've got let statements and where you have mutually recursive functions, mutually recursive definitions separated by the and keyword. And his idea was, we want these applicative expressions to be basically like surface syntax for the lambda calculus, and we need a way of being able to evaluate these expressions in an actual machine. So how do we need that? How do we do that? Well, we need some kind of abstraction for what the machine is. What's that going to be? Well, it's this thing called the SECD machine, which has a number of different stacks for evaluation, control, and dump. So basically, these interacting components are quite easy to implement in a real machine, and they also can be proven to be a useful sort of substrate for the lambda calculus to execute as well. So this was a very big landmark paper. It's also the paper where indentation sensitivity was first introduced to programming languages. So that's quite fun. And there's something else as well. I forget. So there's something else that's original in this paper. Anyway, there are lots of things that are original in this paper. Right. And then in '65, so 1 year later, he extends the applicative expressions language, AE, into the imperative AE, which is where he adds assignment operations to it. And then using imperative AE, he shows a correspondence between Algol and IAE, and then that's how he gives the semantics to Algol. And actually, you can think of this as being the first times anybody did denotational semantics in computer science. Because denotational semantics is this idea that in order to give a semantics, well, let me just take you back a little bit first. Some of this you'll definitely know, but the SECD machine description is basically an operational system that says, here's how the machine moves from one state to the next state. So that's operational semantics, describing things in terms of steps. If you go back to Turing's description of Turing machines, that's an operational semantics. It tells you how the Turing machine moves from one state to another in progressive steps. But actually, even if you look at Alonzo Church's work, he's talking about like beta reductions, which is also an operational semantics for the lambda calculus. So at this point in time, we only have operational semantics. What Landin does is he says, look, the way we should understand Algol is by translation into another language that we already understand. So we already understand the imperative applicative expressions, and that translation is the semantics of Algol. So denotational semantics is about starting with some syntax and saying that the mapping from that syntax to some mathematical object itself is the semantics of that. So we see an early version of this, and then I think something like 2 or 3 years later, we get the work by Scott and Strachey, which shows how denotational semantics can be done formally and mathematically. But anyway, I think it starts with Landin. Landin is known for another paper which is quite famous, which is called The Next 700 Programming Languages, which was written in 1966, where he already foresaw that programming languages were going to just explode in complexity and the number of languages they were. Again, even in the 60s, the number of languages in development was actually quite huge. Everybody was making their own up. So he invents or introduces ISWIM, which stands for if you see what I mean. So there was a kind of a movement in the 60s to having acronyms for every single programming language that you invent, and so that's what he had as his. And the way he understood ISWIM was that this should be church without lambda. That was the subtitle for his talk, for his paper. And actually, it's a paper that encapsulates or more formally introduces a language that he'd been using for a couple of years. So even in the mechanical evaluation paper that we just talked about, he's already using something that is in essence like ISWIM. But there are some details that he wants to introduce here. This was a Haskell predecessor, which had things like pattern matching in it, where clauses, garbage collection, and indentation, of course. So that's a lot of features for 1966. The catch is that it was never actually implemented. It was completely a pen and paper language for a very long time. But to give you some snippets of what it looked like, this could be Haskell. So the stuff on the left-hand side is the ISWIM code, and the stuff on the right-hand side is how he would translate that into the lambda calculus. There's a really funny, at the end of this paper, there's an interesting sort of transcription of the discussion that happened after his talk. And it's really worth reading that because you get an insight into what the big names at the time, how they were thinking. And actually, what's fascinating is that the kinds of questions that they ask and the discussions that they have, they're not all that scary. Actually, these guys were just still discovering what computer science was all about from the ground up. And so anyway, we've got this comment from Peter Noir who says, regarding indentation, in many ways, I'm in sympathy with this, but you would regret it because of the kind of rearrangement of manuscripts done in printing. I mean, is that really the kind of comment that you make? Well, that's where they were at the time, in certain regards. This was a time, you have to remember, before LaTeX, where putting things in print together was not easy. It's not become any easier. One of the key things of ISWIM is that it was equipped with equivalences for reasoning. And by that, basically what Landon did is he identified 4 different categories of things that we would want in his core language that enabled reasoning to happen within the program itself. So he thinks that there should be equations that tell you how sub-expressions should work. So basically, if you've got 2 terms that are equal to each other, then those 2 terms should still, then if you have a function on those 2 terms, then they should still be, the output should also be equal. So this is actually just an application of Leibniz law, which was obviously a lot before that. But he thinks this is something that we should be thinking about in programming languages. The equivalences themselves are essential. Then he thinks about definitions, and there should be equivalences within definitional forms as well. By that, he's saying that the user should be able to write equivalences, that's to say definitions of functions and variables, and be able to do that in multiple ways. So he wants let statements and he wants where statements in this language. And he thinks it's right to have different ways of expressing yourself. And the way that you say, well, these things are equal is by using an equality. Surprise, surprise. But the point is that at this time in history, these things weren't obvious. It wasn't obvious to say that this is how we should define languages at all by using mathematical equivalences. So I think one of the things that strikes me is all of these discoveries over this long period of time, they feel to us like, how could you do this in any other way? But actually, it's the kind of thing where it's easy in retrospect. And a lot of the papers that I write are sort of the kinds of things where I think, well, that wasn't so hard. Well, in retrospect, it wasn't very hard, but actually doing that was difficult. And so I find it very easy to sort of go, well, I'm not really sure if my research is any good at all, or if I've actually contributed anything to the world. I probably haven't. But then if you look at it, you're like, well, actually, no, it was actually quite hard at the time. It's just that now that I look back on it, it's not so much. So I guess, without trying to offend you, I think we're dumber than we think. And that's OK, right? That's how humanity progresses in small increments as we go. OK. The next thing that he wanted to have was equalities between built-in expressions. So with things like if-then-else statements, so this is an if-then-else. He says, if something is true, then do M. If it's false, then do N. And he thinks, well, the way you should define built-in operations is with, well, equivalences again, okay? And then the last one is probably the one that makes the most difference in this language. Oh dear, let me just go forward again. Sorry about that. There's some funny lag between my computer and what you're seeing, I think. Okay, so the last thing that he introduces is equivalences between primitives. And I think this is probably the main contribution of this paper, and it's what the title is after. So let me try and explain this a little bit. It's called the next 700 programming languages because he thinks that up until now, programming languages have been too hemmed in the way they're described. So up until this point, a programming language is, a core language, and that's all it is. But for Landon, programming is about creating small languages, or domain-specific languages is what we'd call them now, that solve specific problems. So he calls these primitives. So the primitives are primitive to the problem that you're trying to solve. And his idea with ISWIM is that the user should be able to define their own primitives that solve particular problems. And so that's why he's saying, look, actually, if I give you a core language that can be easily extended in multiple ways, I've given you a way of creating new languages. And so that's where the next 700 programming languages is coming from. But in order to do that, it's not enough for me to just give you some programming tools. I need to give you a way of defining new expressions, so new parts of your language, new syntax. But also, I need to give you a means of defining equivalences between things within that syntax. So equality, again, is key. So for him, ISWIM is all about, a problem orientation of ISWIM can be characterized by additional axioms. In the simplest case, it's just an ISWIM definition, and he calls these definitional extensions in his system. It's hard to quote Landon because he writes in an extremely terse way. And I think that one of the things that has happened over the course since the 60s is that we as a community have become better at writing papers. But I still think we have a long way to go. And I think one of the problems with the early writings is that they kind of assume that you already know what they're talking about. Maybe it's because there's just a vernacular that's going on in the room and everybody just understands the language and there's just an assumption that everyone knows what the problems are at the time. Perhaps that was true then. But for me, as an expert looking back into the 60s, where I have a fairly good understanding of programming languages, these papers can be impenetrable. They're not all impenetrable. Some of them are really easy reads, but some of them are like, what on earth is the problem that they're talking about here? What's the problem that they're talking about there? And I think this is one of those things where, as you're writing a paper, it's very easy to get lost in your own technical terminology and forget that somebody needs to actually read this, and that person might not be you. So it's great when you're writing a paper to be unafraid of bringing things back almost to first principles, making things easy to read. There's one thing that I like to say, which is it's much easier to write a paper than it is to read a paper. So try and make your papers easy to read rather than easy to write. Okay. And that's not to poo-poo Landon at all. He was like a phenomenal man. So I want to then take us towards structured programming, because where I'm trying to get you is to understand effects. And effects are basically based on a structural deconstruction of a syntax tree. So where do we go for structured programming? The beginnings of structured programming start with ISWIM in some sense, because it was a language that was useful for reasoning and thinking about structured programming in the first place. So Burstall starts thinking about how to prove properties by structural induction in ISWIM. And that's one of the early works on this. There's also work by Tony Horden that goes into recursive data structures, but that's about 1 or 2 years later. And so in this paper, he has an early definition of the concat statement, which almost looks like we would write it today. And he then starts talking about how you would have a function for sorting via flattening trees. And again, this could practically be a functional Perl that we're reading today, right? So this was very early work. And furthermore, he has a proof of its correctness by using induction. OK, the idea of structured programming, the idea that you can make good progress by looking at some data type and then mathematically, by induction, proving properties of that thing, becomes a really big idea. And it's popularized in '72 by Dijkstra, Hoare, and Dahl in this wonderful book called Structured Programming. And I guess today it's something that it's a technique that we all know about and would use very easily. So that's one big thing. And I think the key quote from this book is that there are certain close analogies between the methods used for structuring data and the methods for structuring a program which process that data. And we continue to exploit that. One of the other things that came out of Landon's paper was actually an early denotational semantics, and I've already kind of touched on that. He makes that really clear when he says that, so there are these three clauses that he talks about for what it means to be denotational. So first, so I haven't properly highlighted that, but is this working? Oh, so there's a 2-second lag between what I'm doing and what's going on. So this is like a really difficult video game where you have to, okay, I'm not going to play this video game anymore. The point A on the slide says that each expression has a nesting sub-expression structure. If we look a little bit further forward to the 1971 paper by Scott and Strachey, you see this equation here, which is the first rendition of what it means for something to be denotational. What this says is the valuation of the expression v0 plus v1 is equal to the valuation of v1 of v, so the valuation of v0 plus the valuation of v1. If you look at how Landon's description of things it basically corresponds to this equation. So part A says that each expression has a nesting sub-expression structure. So the expression in this case is v0 plus v1. And the nested part is that you've got a v0 and a v1 on the right-hand side. So that's the first thing that he's talking about. B is each sub-expression denotes something. So v0 should denote something, v1 should denote something. Well, on the right-hand side of the equation, you have the valuation of v0, that denotes something, and the valuation of v1, that also denotes something. And part C of what Landon is saying, he says, where is it? The thing that the expression denotes, i.e. its value, depends on the values of its sub-expressions. So the thing on the left-hand side, the valuation of v0 plus v1, should be a combination of the valuations of the things on the right-hand side. Well, in this case, it's addition. So he's exactly describing denotational semantics, but he hasn't done so using a mathematical equation at this point. That happened much later when Scott and Strachey start thinking about what domains look like and how complex all of that is. Okay. So let me kind of draw us back to this dichotomy of functional versus imperative programming. So what I'm trying to argue is that from an early time, Landon saw that this dichotomy shouldn't really exist at all. That actually we can have programming languages that have both, right? So he's got the imperative applicative expression language, and he's thinking about this in terms of the lambda calculus from the go. And he says that ISWIM brings into sharp relief some of the distinctions that the author thinks are intended by such adjectives as procedural, non-procedural, algorithmic, heuristic, imperative, declarative, functional, descriptive. Well, here's a suggested classification in the new word. So what he's saying at this point is that there is this idea at the time already that there is lots of different programming styles that are not imperative. So all of these things are unimperative programming languages. But what is the thing that draws all these things together? Well, his new word is denotative. So denotative programming is the antithesis of imperative programming. So imperative programming is giving statements about how things should work, or in an operational setting, whereas denotative is giving a denotation to things. I think today we might, instead of saying denotative, we might say compositional, perhaps. But I think the ideas are essentially the same. And denotative is a perfectly fine word to describe the non-imperative things. It's funny because I gave a talk at PADL yesterday, and so that's the practice and applications of declarative languages, and it's about declarative languages. And I thought, well, I'll give these guys a definition of declarative languages to start the talk. Let's see what people have written about what a declarative language actually is. And the definition of declarative is just not imperative. Which I think it's kind of sad, right, that we're defining a concept in terms of not this other thing. Where I think Landon is trying to be constructive here and say, actually, it's denotative. It's stuff that you can construct out of the constituent parts. I think it's a much more useful classification. Okay, so perhaps there's this sort of nice synergy between side effects and pure things going on where you can define one in terms of the other. They're not in conflict. So I think that Landon saw that at this early time. Okay. So what this would require would be a denotative way of expressing side effects that supports reasoning. And that's what I think we get with monads. So why do we have a picture of a burrito here? Well, this has to do with internet folklore. It's because of Brent Yorgi and his post in 2009 where he explains that monads are like burritos. Actually, in his defense, he explains a hypothetical person, I think, called Joe, who thinks that monads are like burritos. I don't know whether Brent himself thinks that monads are like burritos. He assures me he doesn't. But because we're doing history, I want to take you right back. And this is South Africa in 71,000 BC. This is not a joke picture. This is actually a rock that was discovered in that region that dates back to 71,000 BC. We've got scientific papers written about this thing that shows that if you look at the inscriptions made out of ochre, they correspond to something that could only have been man-made. And this is truly the oldest thing that has been found that's been written on. Isn't it magnificent? But if you look very closely at these detailed lines that we have here, you might realize that mankind has been striving for Haskell for a very long time. Let me show you another artifact from South Africa in 71,000 BC, which is this beautiful picture of basically the Haskell committee getting together and coming up with all the ideas that they had. Actually, Haskell was very, very closely related to Miranda, which was its predecessor, and which was conceived by David Turner, and itself was very similar to IceWim, but nevertheless, this is the committee. And there's a really lovely paper written in 2007 about a history of Haskell being lazy with class. I really recommend that you read that. And one of the sections in that paper talks about monads as input and output. So the original version of Haskell did not have monads in it. So there was no way of doing I/O in the way that we do it now. What they did have was I/O as being done through streams. So the idea is that Haskell is a lazy programming language, and you can have a stream of input, which is all the input that the user will give you, even the stuff that's in the future. And as you demand that stuff, well, maybe it will arrive, but if you keep on waiting, eventually something's going to come down on this stream, which will be the input that comes from the future. And then what you need to output back out is this infinite stream of things that your program does. And so you've got this, these two streams of requests and responses. And functional programming is just a function from requests to responses, right? So that was the original model, and it was a little bit awkward because it was hard to extend in the sense that you had to be upfront about all of the ways in which the language could interact with the system itself, which you had to embed as a data type. So monads sort of fixed that problem and made imperative programming something that was part of the design of the language from the go. So what is the history of monads? Well, monads are, you can tell from their name, they're clearly not made by like normal people. They're invented by mathematicians and part of category theory. So the classic reference here is Saunders Mac Lane, who basically founded category theory. He says something like, the recognition of the power and simplicity of the use of monads and comonads came quite slowly and started with homological algebra. And so he points to Mac Lane's work in '56, and so I dug that up. And here is the first description of monads in French. And if you look at it closely, this part of this paragraph is the only part that I can find that actually describes monads, which says, nothing to do with monads if you look at it, except it is exactly a description of monads if you understand homological algebra and you understand how these things are built up and something called the bar construction. But to the layman, this just looks nothing like what we would recognize as things. And again, what I'm trying to point out here is the refinement of concepts takes a long time. We had Landon with a textual description of denotational semantics, and then something like 5 years later, we've got Scott and Strachey turning that into a crisp formula that we can really parse and understand quite quickly. Here we have a description of monads, which is not only in French, but quite difficult to decipher. and yet does describe monads, but it takes some time before things advance. In fact, it takes Roger Godement to simplify things in this paper in '58. It's still in French, but it is understandable. I joke because I am French, okay? I'm allowed to say what I want. So here we've got the fundamental construction of things, and we can see that K, so this symbol, if only I could point K down here, has arity 0 to 1, which is return, and then P here, oh, I've made it bigger. P is join. And so here we have the join laws quite clearly written. So for years, monads were not named anything scary. They were simply called standard construction, and then maybe fundamental construction, and then they were just called triples for a long time because they consisted of some type T with some K and some P, and that was it. So they were kind of boring and not understood. So I think it's natural for me to ask the question, well, where did monads come from? Why are we using this word in the first place? And so with that, we have this chap, Jean Benabou, to thank. So in '67, he introduces a paper where he talks about monads more carefully. They are a play on the word monoid, but also they preempt polyads, which are a further extension that he's playing with. And so he says that the choice of monad actually comes from this example, and polyads are this extension. OK. So how did we get here? Oh, we're trying to think about monads in the context of computer science. So how did we get category theory in computer science in the first place? So a lot of category theory started actually at IBM for computer science, where Samuel Eilenberg and Wright started thinking about automata in general algebra in terms of categorical constructions, and they use universal algebra and Levert theories to describe these things. Now, Levert theories are basically a way of describing operations and equations between those operations, which turns out to be a useful idea to this day. I think I'll probably skip through this. A little bit further on, in '71, Elgert starts thinking about monadic computation and iterative algebraic theories. So he connects Levert theories with Turing machines. So that connection to monads started in '73. And it's quite an interesting story how category theory really exploded in computer science. So McLean, in something like '70, talks to Goguen and says, well, maybe you should apply for this fellowship at IBM and spread some of the categorical ideas there. And so Goguen goes to IBM and forms a group called ADJ. They want to write under a pseudonym and create like a new foundation for computer science from the ground up, a la Nicolas Bourbaki. If you don't know Bourbaki, Bourbaki was a French mathematician who basically rewrote a lot of algebra in terms of universal constructions or simpler constructions. But the thing is that Nicolas Bourbaki was not a person. Nicolas Bourbaki was a complete invention of a bunch of mathematicians who wanted to write under a pseudonym. And so similarly, these guys wanted to write under a pseudonym, but for various legal reasons, I think we're just not far after Cold War territory. They weren't allowed to publish under like some random person's name. So they came up with this group name ADJ, which stands for junctions, which was a terrible joke. But they write a paper called A Junction, which is what they're named after, between computer science and category theory part 1, and then they had part 2, and they had like, I think 6 parts outlined on how this would go. And the project was huge and influential, but they actually never completed it. I think they never made it past part 2 of their entire thing. And so maybe that's another lesson from history for us to think about, which is it's really fun to start a great grand project and be like, oh, we're going to rewrite the whole of history, or we're going to rewrite the whole of this thing. But maybe we should just sort of start in small increments and just see how things develop. I'm thinking of Knuth and his wonderful tomes, but I don't know when they'll be completed. So yeah, they never made it past report 1 and 2, even though it was hugely successful, and Knuth's books are hugely successful. Perhaps there is something good in having a huge rewrite, but maybe you don't need to announce up front the next 15 chapters of your thesis. So where do we go from here? Oh, right, yeah, so the idea of category theory and what we call initial algebras, so proving uniqueness from from syntax comes from Burstall, who worked on structural induction earlier, and Thatcher, and they start thinking about algebraic theories and how they correspond to recursive functions. So they used monads to explain stateful programming. So they say we have a principal example, recursive monadic program schemes, which described are intuitively below, and then they carry on and do the connections there. And then here we have sequential composition of programs corresponding to monad sequencing. So they know that monads are good for sequencing programs back in '75. Monads in the Lambda calculus is kind of the next big development. So Dana Scott writes this paper relating theories of the Lambda calculus, and he basically says, he asks himself, what is the theory of functions? And for him, the theory of functions themselves is category theory. And so he writes this paper, Eugenio Moggi picks this up in 1980 and says, oh, hang on a minute, we can use these ideas as a foundation of effects and computation themselves. And that happens in '88, where he talks about a Lambda calculus which has things like state encoded into them. So side effects with state exceptions are all modeled with monads, but they're used as a way of modeling these features of the Lambda calculus rather than as a means of programming. So as a means of programming in '91, he writes another paper that shows that the notions of computation in programs, like partiality, non-determined side effects, exceptions, and continuations, can be modeled monadically. He doesn't actually sort of do programming. He just says that these programming features can be modeled that way. But for the story of effects as a programming feature, we go to '85, where Wadler is thinking about how you can deal with exceptions in a mathematical way. How can you program with exceptions in the first place? But he's not talking about monads. He's talking about using laziness as a means of capturing exceptions. I want to skip through this. In '88, although published in '90, Spivey picks up the theory of exceptions and says, actually, the way we do the functional theory of exceptions is by using monads. And so he introduces the maybe monad, and the words just and nothing are due to him in this paper. He introduces return, join, and bind, and shows how these are programming constructs that you can use. So that's what happens in '88. Wadler picks up on this idea. Oh, but before that, monads in programming continues. So we've got the work of Richard Bird, where he's thinking about how you can have a calculus for functional programming happening in '86 and '87 with useful properties. So these are properties that we would use quite often today. And then Spivey notices the connection between what Bird is doing in category theory in '89. And then so he continues to use monads as the underlying, or he conjectures that monads are a good way of dealing with the underlying theory. And he's not wrong, and he ends up sort of having a construction that's close to what we call the free monad, which we would use today to describe syntax. Okay. So for monads in Haskell as popularized today, we turn to Wadler, who wrote a really important paper in 1990, which was sometime after, a year after the introduction of monads by Spivey. And what he does here is he introduces a whole bunch of really useful examples that show you how to use monads in programming. So, and the point that I want to make here is that although the ideas were kind of already there, that wasn't the end of the research, right? It was just the beginning of things. Wadler then took those ideas and showed you how to actually use and apply these things. So there is a lot of value in just explaining something that you feel is sort of obvious. I think Spivey knew how to do all of these things, but Wadler actually popularized that and made it really important for us today. Okay, I'm quickly running out of time. I think it's...
You can have an extra 10 minutes.
Wow. Okay. Okay. I will try to. I will wrap quite quickly. So, monad transformers are the concept that we would use today to write things, and type classes were introduced by these chaps in '89. They led to constructor classes. I think I just want to whiz through this and just sort of tell you that, again, it just took a long time before we got to the point where we could actually use monads as a programming concept that we have today. But the problem has always been modularity. I wanted to pick up on do notation, which was, again, first given by Launchbury where we would be writing Haskell with curly braces and semicolons to do imperative programming. But the actual implementation was by Jones in '94 in a language called Gopher, which was one of the early Haskell compilers. And for lexical reasons, he introduced the do keyword to make things work out, which I'm kind of sad at. I preferred the non-do version of Haskell, but there we are. As I said, do notation is syntactic sugar. Syntactic sugar was a term invented by Landon, as was indentation-sensitive languages. The last time I gave this talk, this slide didn't exist because I did not know where the origins of bind came from. But thanks to the internet, somebody very kindly posted on Reddit that there was a post on Twitter. So thank you, Iceland Jack, for pointing me to this post on Twitter, where Andrew Gordon said, 30 years to this day, he submitted his PhD thesis, and the bind symbol is the longest-lived survivor. So perhaps the lesson for us here is that although your PhD will be, born out of sweat and blood and years of sweat and blood, maybe you'll have a contribution as tiny as 3 characters. But actually, that is not the purpose of the PhD. The purpose of the PhD is to grow you rather than to make an impact on computer science. Some do bigger than this, some as much as Andrew Gordon's 3 symbols. And so here's a copy of his thesis. Here is the first use of bind that was published, and he says that comes from where you think it does. He'd been using this right triangle, which is how I was taught bind as a symbol, through some earlier work in '89. And here we have what I would call the free monad for concurrency, but that's not what he called it. He just used it as a data structure. And he saw that it was easier to type right than triangle, and he wanted right equals to mean bind because there was something to do with equality going on there. OK, so that's where that came from. And I want to just wrap up with effect handlers, which is the stuff that I do, which basically says that syntax and semantics are the way that we should give is the way we should program with effects. And so I'm just going to whiz through this very quickly. I don't expect you to understand actually much of this talk at all. But the syntax, so the idea is that we start with the syntactic programs, which are basically trees, and we can handle those into expressions that evaluate those trees. So that's denotative. And why do we like them? We like them because the operations are algebraic. They have nice properties. They're extensible. You can add things to them. They're modular, which means that you can handle things over and over. They're flexible. And there are multiple semantics that you can give. They're equational, which means you have some systems of equations. They're pervasive. They're absolutely everywhere. And they're efficient. So there are lots of reasons why I like these things, but I'm not going to go into any of that. They are based on these things called Levert theories. Levert theories go back to universal algebra. John Power picked up on this idea and thought, well, it's good to do operations and semantics in that way. Plotkin and Power go into algebraic operations. And eventually, we have Mattia Pretnar, who was a PhD student working with Plotkin, and he invented algebraic handlers, or handlers of algebraic effects. And then we get into where we are now. So after that PhD, a whole bunch of things happened. And so now the bibliography since, and notice this since 2009, is quite enormous of things that we could possibly cite. And so that's where my research starts. We've got higher order effects coming into play. And really, some of this is interesting because it was me meeting. It became important when I met somebody called Rob Ricks at ICFP. He was working at GitHub, and he was saying, well, we're using algebraic effects, but things aren't really working with everything. How can we make it work? And I said, sounds like what you need is scoped effects. And so I showed him some of the work that I'd been doing with some co-authors. And the idea is that although you have effects, sometimes you want to interpret your program in multiple ways. So you might have a non-deterministic program that you do depth first, breadth first, or depth bound, or you maybe just want one result. But these depth first, breadth first, depth bound, and once are normally treated as handlers in the effects world. And I thought, well, it'd be useful if these were operations in their own right. The point is that we wanted to abstract those into some kind of syntactic construct called search instead. And that became the idea of higher order effects. Where are we going with this now? I don't think I really care about you understanding a bunch of equations. Let's carry on through this. I showed them that work. they were worried about efficiency. That was something that I had also written about. And it was 250 times faster than the previous attempts that they had. And so they shipped it. And that's what GitHub used for semantic analysis of lots of programs that you'd submit. OK. I think this is the conclusion. Oh, yeah, right. So there are now a whole bunch of effect libraries, which we can just whiz through. I think the state of the art is that there are lots and lots of different implementations of these, none of which are ruling. So to conclude, we've seen like a whole bunch of history that I've summarized very badly, starting from 71,000 BC. What I hope to show you is that the development of computer science has been long and arduous, and hopefully you can be part of that. So what next? Well, I think that's a question for you. So good luck with your PhDs, and I hope that your research goes well. Thank you very much.
Thank you, Nick. I think we have time for a question or two.
Hi, first of all, thank you for the talk. I just want to ask, like, if you have anything to say about how we can kind of balance looking to the past and through all of these ideas that you showed to us versus just new ideas and
Yes.
yeah, how much should we be looking to the past versus?
Okay, you're asking me after this whether how you should balance looking into the past. And I say that sort of almost seriously. So as a PhD student, I would love digging into the old historical references to stuff and just getting utterly lost in what is an absolutely vast literature. I think that was a mistake. It makes for fun talks. But I think that I would have been better off focusing on just my own ideas and developing something that I thought was cool now. And it took me a long time to recognize that. I didn't need to understand all of history before I could make a contribution. So I think that my encouragement to you would be, when you've got an idea, almost always that idea will be novel enough. And once you work on it and develop it, you should be aware of the literature a bit. But I think when you're exploring, just understand your own idea well. Then, as you're understanding that idea, start writing a paper about it, start doing a literature review, and then you'll think, oh, that connects to this. And with almost every PhD student I've met, they think they've been scooped. And actually, often the case is, yes, that there is related work. Thank goodness other people have had that idea or similar. But actually, you can probably extend and change and develop or have your take on that idea. Or there's almost always something different that you can do. There's always a different take on things. I think research is extremely fractal. So you've got the big broad strokes written in the 60s and 70s. And since then, we've been refining those strokes as we go. And there seems to be no end to that. So I would say, be cognizant of history. Make sure you make sure that you refer to things properly. That's really, really, citation is essential. But don't be afraid to just like pioneer into your own research and be a little bit blind to what's going on for a while, and then sort of emerge and then have a look at what people have done.
It's just one thing was, yeah, I guess you mentioned sort of algebraic effects, and you mentioned that, like, say, GitHub rolled that out to production. So, like, how long did it actually take from, like, the first? So I think it probably came up, but it was went through very fast.
Yeah.
How long did it take from, like, the first, I guess, theoretical proposal of algebraic effects to the first actual industry deployment? Because I know there's, like, huge variance in, like, how long it takes these ideas to trickle down from academia to industry. Like, what speeds this up? What slows this down?
Yeah, that's a really good question. I think it took quite some time. I think it depends on exactly what you're asking. So I think my work on this stuff was in 2014, and then the chat with Rix was maybe 5 years later, and their implementation was basically started as a copy paste of the stuff that was in my paper. And then they engineered it amazingly well to make it work. But I think that engineering took them a few months of production, or maybe I think he had an initial version in 2 weeks, and then they worked on it for a couple months after that. So that part was extremely rapid. But the actual point at which they started using it, that took a long time, like that, to actually go in. So yeah, I don't think despite what grant writers kind of make us do, I don't think we should care about impact in industry almost at all. Initially, I think we should just be interested in interesting ideas and things that work well, and then let industry catch up. They don't be over-focused on reaching out and trying to like make contact. But I mean, what do I know? I'm not very good at this. So like I think the ideas are more important than the industry. Yeah.
All right, let's thank our speaker. And we have a break now, and we'll reconvene in this room at 11.
This is the second session of PLMW, and it's my great pleasure to introduce Nikki Vasu. She is at India, and she created Liquid Haskell. So she's going to talk to us about Liquid Haskell and refinement types.
Hi, so thank you, Leo. Thank you very much for having me here. So yes, I am going to talk about refinement types, and mostly in the aspect of Liquid Haskell. I'm going to show you a demo. So how many of you know what are refinement types? Okay. I hope you don't find it boring. Okay, so for those of you who don't know, so the concept is quite simple. And it is that refinement types basically refine types with logical predicates. And this is a standard example, like the most used example of refinement types. So I am starting from an existing type. I confirm that this doesn't work, the laser. So I'm going to start with an existing type of list indexing. And I'm going to refine it with a logical predicate to encode safe indexing. And in this case, I'm going to name my argument. So I'm saying that the first argument, the list that I'm indexing, is called x's. And then my index is called I. And inside the type of the index, that is an integer, I am refining to say inbound indexing, right? That the index is between 0 and the length of the list. And then that is showing me safe indexing. So this is a basic concept. And I'm going to show you an example of how refinement types work. And for that, I'm going to use Liquid Haskell. That is, enter full screen, I hope. So Liquid Haskell is a refinement type checker on top of Haskell. So here I have a Haskell program. And I have my Cabal file to build the program. And all I'm doing is in the Cabal file, I'm using a plugin, and I'm saying, OK, like every time you compile your program, use the Liquid Haskell plugin to check everything. And by default, when I check things with Liquid Haskell, it has some built-in refinement types, like safe indexing. So every time I am indexing a list, Liquid Haskell will use the refinement type, and it is going to prove safe indexing. So like here, I have a test. It takes as input a list of integers, an integer I. And what I'm going to do is I am going to index x's with I. I click save, and I am getting refinement type error. And like we are still at the word that the error messages are simple, so they make sense. And this error says, you know, I'm expecting the index to be a positive, a natural number, and I got a value that is I, for which I know nothing. So there are many things I can do here. And the simplest one is I'm going to use a branching, and I say if your index I is indeed greater than 0, then go do the indexing, else 0, as suggested. And now I like the error change, so I can come and refine it more and say I want it to be greater than 0 and I less than the length of the list, and the error got away. Nice, right? OK. So of course, I don't want it to return 0, so I can say return nothing in the other case. In the then case, I am going to return a just. And I return a maybe. So generally, the Liquid Haskell's refinement types work with many Haskell concepts. OK, what else we can do as an example? So we indexed an element from the list. And like the standard built-in that have refinement types are like safe indexing. What is the other most common error that you see in the verification world? Like most common error that exists? What? Yeah, but something very, very simpler. Division by 0. Yes. So division by 0. It is like if you want to give a very explanatory, like I did this to verify it, like try division by 0. It's the simplest thing. OK, so I get an index. I get an element from my list. It is an integer, so I can go and say, OK, 42 divided by whatever I got. And Okay, so division has the precondition that says your second argument should always be different than 0. You cannot prove that. So how can we fix this error? Okay, so I can go and give a refinement type for my arguments. And like, I think for me, the most essential feature of refinement types, as opposed to other verification things, is you can go and refine the types no matter where they exist. And this no matter where it exists, it's very cool because here I have a list of integers, a collection of integers. And I can go inside here and say, the collection of integers are all of them. They are different than 0. And now, like, I know that if I get any element from my list, it's different than 0. And so division by this element is good. And this is very good because if I didn't have the power of refinement types to go inside collections and refinement, then I have to deal with for all elements of the list. Like, for all are like dangerous for verification because you miss automation somehow. OK, and now since we went and we put a refinement type for this list, I am going to also give the precondition so that I can get rid of this runtime check. Right? So I can say that I have an input list of integers. All of them are different than 0. I'm going to name this list. And then for my index, I'm going to name it I. And I'm going to say this I is less than greater than 0. And also I is less than the length of x's. And now I have the precondition that I need to go index. So I don't anymore need this runtime check. So I can go and remove it. And verification is good. And I can also remove the maybe. OK. And hopefully this is good. OK, these are the two very standard examples of refinement types. They're very good for safe indexing or whatever has to do with integers. Division by 0, they can prove it. And are there any questions? Generally, yes?
Is this all done without dependent types?
What do you mean dependent types? I cannot go past this.
Well, it seems like a lot of what you're doing can be achieved in a dependently typed language by creating types which have these restrictions.
Yeah, so for me, it is like exactly. Yes, that I can do. Like the question is if this is done with dependent types, and that I could do all this in a dependently typed language. So I think like one of the historic answers is that refinement types are like lighter way of dependent types, because I don't want to go and use the whole like dependent type language, because usually it requires a lot of proof terms provided by the user. I want to have like on my own programming language that I know, like here Haskell, like there are other. I want to be able to use concepts from dependent types, and I want to be able to have automation, like to have like type checking automatically by external solvers that here I'm using an SMT to decide all this. But like my original question is like, if like you use the abstract idea that dependent types are types that depend on values, for me refinement types is a subset of dependent types.
Thank you very much.
There was another question? Yes.
I know, for example, for example, for like a dependently typed filter function, you end up with like, you don't know the length of the list after you filter. How is that handled with like refinement types?
So in refinement types for filter, the standard thing is you can say that the length of the result is less than or equal to the length of the input.
Oh, okay.
Yes, but the idea is like even for let me see, like even for this simple take function, like you lose the information that you took an element from your list. So refinement type checking is not complete, in the sense that you give your specification and they can be as abstract as you write them down, but then you cannot prove every property that your program has.
So just on that note, it's not possible to express that the return value is somehow the return value is somehow present in the list. It's not possible to express that in refinement types. Is that right?
So you can say it because in Liquid Haskell we use set theory because this is decidable and we have allowed it. So you can have a post condition that says that whatever I return is an element of the yes. But again, the concept is you can express as much as you need, but the more you express, the more sophisticated properties you're going to prove, the more work you have to write down. Yeah.
Yeah, I mean, yeah, just very dumb question along those lines, but like, yeah, does Liquid Haskell does it fail gracefully? Like degrade gracefully? Like if you can't prove the thing, can you add any sort of hint, or is it like just, oh, SMT, either it will sort of satisfy or not?
So does Liquid Haskell fail gracefully? So I was very proud in this very simple example. The error messages were very graceful, on my opinion. So then we go to the deep file. We'll go there. That we're going to prove more like type theory stuff, like very more difficult properties. And there it does not fail. Like the error messages are very bad, but like we will see a concept that lets you prove anything yourself. But you are kind of on your own.
Is there any way to express like relationships between two different objects? For example, like these two hash maps have the same keys, something like that.
You have to, yes. Yes, let me go to the deep, because maybe you will, yes, like there are these questions like how much you can express and like, yes, error messages. So like, so the light is the standard usage of Liquid Haskell that I suggest like you can use now, like if you want to prove very simple stuff, it works, everything will work, error messages are good. But then we have all these questions like, can I express more? Can I prove more interesting stuff? Can I help SMT like do stuff? So like a long line of my research is addressing these things. And we developed Liquid Haskell to be able to prove like more sophisticated properties. And the standard sophisticated property is here that list is right identity. So I am expressing this here in refinement types. And concretely, I'm saying right identity is a Haskell function. Undefined proves everything. Because we are not in a type theory, we can have escape routes. And right identity is a Haskell function that takes as input a list and returns unit, like no runtime value. But what I'm doing is I am naming my input x's, and basically this is a shortcut for my result is a value that is unit that is refined with the property that I want to prove, right? That x's append to the empty list returns the empty list, and like again, like syntactic sugar for Liquid Haskell. If the value is not important, I can go and ignore it. Okay, so how do we prove this? We are going to prove it like as a mathematical proof by induction. So I have my base case that is fine unit, and then like Copilot is amazing. Fine, if it insists, I can put the right identity because I assume most of you know that like I'm going to do inductive call. Okay, and here the error messages are useless. The only thing that it's helpful, it says there is an error in line 12. So I'm going to line 12, and it says unit cannot prove this property that you want. So how do I do it? I am copying paste the property, and I am using some proof combinators that come built in from Liquid Haskell, and says this I want to prove equality of x's, where x's is my empty list. If I'm going too fast, let me know. And then again, from proof combinator library, there is a concept that says, and this finishes the proof. And this is enough to prove my base case. Just basically, this is rewriting. This is evaluation of append. So evaluation of append on empty list proves my my base case. And now I want to prove my inductive case. And again, like my proving style is copy paste. So x's, I am using my equality. And then I want to finish my proof with QED. And it says line 18. Line 18 cannot do that. And as Copilot insisted, I am going to tell it, OK, this step goes by right identity on x's. And before. So this step, this is equal because of right identity of x's. Right, so I am using some operators that are defined in proof combinators library, and I am encoding my proofs as Haskell functions. And the proof is done, and like Liquid Haskell comes with a totality check. So if I want to omit my base case, it's going to say totality error. Again, you have to search for it, but you can see a totality error. And termination error, so because my functions are total, my functions are terminating, then there is some trust that you are encoding indeed proofs by induction, right? So that's all good, but of course, automatic verification doesn't like to do this evaluation, like the easy evaluation steps. So we have developed a technique that is called PLE, proof by logical evaluation. So these are comments. If I do the the comments are interpreted by Liquid Haskell. So I activate proof by logical evaluation, which means I do not need to do the steps of evaluation. So my base case is just performed by evaluation. So I can say just unit. And this is all good. My inductive case is evaluation, inductive call evaluation. So I still need to keep my inductive call, and the rest evaluation steps are going to automatically be figured out by proof by logical evaluation. So my inductive case is just my inductive call, and I can remove the rest. And here I have, oh, go away, I don't want you. Yes, and this is a proof of right identity. Cool? Cool. And this PLE, proof by logical evaluation, I think it's very cool because it lets you like hope that proofs are figured out by logical evaluation. So for example here, I am going to prove that append is associative. What does this mean? I want to append x's, y's, and z's. On the left-hand side, I first do the y's plus z's. On the right-hand side, I'm appending x's plus y's first. And I want to prove that. And if we have done some proofs, we can assume that this is just proved by induction. And I have PLE on, so I have Copilot on. So my proof is auto-completed. Cool? Nice, let's do one more. Yes.
Familiar with Haskell syntax? This is something that's been bugging me.
Yeah.
Is this a valid Haskell file?
Yes.
So can you, in Haskell, you can split the definition of a function in many places? Like what? Okay, I see. That's what's happening on line 32 and 33.
32 and 33, yes.
Huh?
Yes. So ASOC is like it's a case analysis. So I could say x's, and then I can say case x's. Yeah, exactly.
And the two are the same.
These are totally equivalent. Yeah. So if you're, they are equivalent though. Part of some scoping things. Yes. Why is this? Yes, these two are totally equivalent. The Haskell way of writing is splitting. Other questions? Yes.
Those special syntaxes you have for proofs, equal, 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 star, 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 QED things, do they have a semantic in terms of just Haskell, executable Haskell? I mean, can you just run the file, or do you need to eliminate all of that before having an executable file?
No, so all of these are Haskell functions that are defined and imported from proof combinators, and they are actually quite simple. So for example, the QED is a data. That is just QED. And the question mark takes something x and y and returns x. And what else did I use? Yes, equality again. Like I'm just combining stuff. So I mean, yes, but the short answer is everything is defined in the proof combinators library that comes with Liquid Haskell. You can execute, and they are defined so that they don't really affect your runtimes, but they pass the information to the solver. So the information exists there.
Yeah, so it's a proper Haskell
It's a proper
DSL, right?
It's a proper
And
Haskell file, and again, like I have my Cabal file, and I tell it use liquid Haskell every time you run it.
And does it do runtime checks or not even? Like
No.
runtime checks that some things are equal, that you asserted they were equal or not?
No, there
Fully
is no runtime
transparent.
check because liquid Haskell is using the Haskell compiler GHC to develop and to take all the information, but GHC does not know about liquid Haskell. So, I mean, when we started, we said, okay, we are going to take all this information and eliminate checks from GHC, but telling GHC how to interact with liquid Haskell, I think is it's a nice project, but it's a lot of engineering. So, like right now, GHC does not know about liquid Haskell. Okay, let me do one more proof. And that's a more difficult one, distributivity of reverse and append. So I have the append, we saw it, and I am saying that if I want to reverse a function, x is appended to y's, I first need to reverse y's, then I need to reverse x's. Okay, let me try to do that. Oof. That's too smart. Okay, distributivity, I'm saying, okay, I'm going to do it by the standard proof by induction. This does not work. I have some time, I guess. Let me do the base case. It's like, how many of you know this proof? Okay, so let's do it. Okay, so if you know it, like how do we do it? Let me do it directly if you know it. Okay, so base case, do I need to use something like, is there somebody who knows, or should I just write it? There was some hands there. Shouldn't we just evaluate? Okay, let's evaluate. It is this proof that it... What's that?
You need the symmetric case of the proof that you had before because you're going to have plus the empty list on the right-hand side.
Plus, so I need the right identity.
The right identity, yes.
Okay. Let's see. Right identity of reverse y's, right? So this is reverse y's. And my error went in line 50, so this actually worked. And okay, so I am saying I'm going to do the inductive, like in the cons case, my inductive step, I am going to use my my inductive call, my distributivity, and yes.
Maybe you need the associative
on.
So I guess. Oh, thank you. I guess you'll have like y's and then singleton x and then reverse y's and then singleton x and reverse x's.
Reverse y's, reverse x's and singleton x.
Sorry, flip the reverse x's and the singleton x.
Oh no.
Or maybe that works.
Let me
Never
see
mind.
if the flip is working too. Okay, no. It's okay, yeah, I knew this is a smart audience. Okay, so yeah, that's the proof. I need the two helper lemma that I used. And so as you saw, it's like, so there are two difficulties in this kind of proofs. First is that you need to know exactly the lemma that you need to use, and then it's like, what arguments, how do I call them? So Liquid Haskell comes with one more like smart tactic, and it's called like rewrite with. So rewrite with is telling me that it was off, now I'm turning it on. It's telling me to prove distributivity, go use associativity and right identity. So now I can remove the calls of right identity. And the cool thing about this, like the difficulty about this property, I can also remove that, is that you don't, like you need to know what you're going to use, but you don't need to know exactly the arguments because like not everybody can remember. It's difficult. So this is the second tactic, and like again, in like other provers, this is on by default. But like Liquid Haskell lets you have control over it because otherwise things are getting very, very slow. Yes?
How exactly do you use these proofs in a program? Do you just like call the distributivity function in
Yes.
like in some other function where you need that property, or?
Yes, the moment that you call it, you have the refinement, it's there, and the SMT sees it, and like you can use it in your programs. So like this was all the, so the goal for me is like do the light stuff. As a programmer, you're going to need some light stuff, but at some point, like to prove the light stuff, you're going to need that append is associative. So you can prove it separately and then call it. But if you, like these are like slow to run. It's better if you don't run them.
So earlier when you showed us the proof for the properties of write ID, you explicitly wrote some evaluation steps that you wanted the type checker to do. But here you're relying on some properties of reverse, like the fact that reverse, you pop the front element of, and then you append it at the end, and then you use this for the when you want to apply the associativity rule. So are these lemmas that you've already proven which are now being automatically applied here, or is this using the definition of reverse that it's automatically doing this evaluation?
No. We proved the lemma, and now we are calling the lemma that we proved before.
No, but I mean the actual property of reverse itself, like how it's defined. Is this from the definition of reverse?
No,
or?
like I have it here. I have to redefine reverse.
Oh, okay.
Because like in the first proof is like by evaluation, so I need to have the definition.
In this file?
Yeah.
Okay.
I mean, I can improve. Okay. So I have like, this is all the hidden stuff I have. But this is all. I don't cheat. So I have to prove them. And so the important thing is that I need to reflect them. Reflect means the definition goes in your logic, basically. In your, like, Liquid Haskell has access to it. I can import things, but I need to have them reflect them in the other file. So I cannot import from Prelude. Yeah.
This could be a dumb question, but because you may have just addressed it. Also, I may just not understand. But can you like nest, once you've defined these distributivity and stuff, can you use them in your logical formulae to define refinement types?
Yeah. If I can use distributivity on my refinement.
Yeah, once you've like defined a function using refinement types, can you then use that in the logical formulae?
So I can use in the logical formula things that I have reflect.
Right, so you then have to
use,
reflect
and then this goes like to, like if I write, like I can reflect only things that either are constants or use other functions that are also reflected. So like it's a closure property. So I can define foo, I don't know, 42. I cannot put foo here, no foo. But if I reflect foo, I'm destroying. If I write reflect foo, then I can use foo in other reflected functions, and everything that is reflected, it can go in my refinement.
I guess what I was trying to ask is, in the logical formulae, do all the functions that you use to define it have to be normal Haskell functions, or that you've reflected, or can you use the functions that you define using refinement types after you've defined them to put them in your like? Can you then reflect? You said that you can only
First I define, I reflect, and then I can put them in my logic.
Okay.
And then
Okay.
And I can reflect proofs. I can reflect many things.
Okay. Thank you.
Okay, I do have some slides. Okay, last, and then I do go in my slides.
I assume you have to make sure reflected functions are total.
Yes, its totality is on totality and termination, and by default on in Liquid Haskell. You can turn it off if you know what you're doing. Okay, let me go in my slides. I'll try to be very quick. I have 15 minutes, right? Cool. Okay, we saw that, and this is more or less how refinement type works. It takes as input a program and some properties, and refinement type is a tool that is generating logical formulas from the program and the properties, And it says the logical formula is an SMT solver that is a tool that automatically decides validity of logical formulas, and it returns true if it can prove that the program satisfies the properties. Otherwise, it returns no. And like we saw a property at the beginning, we saw the safe indexing. And at the very, very first example, we tried to prove that x is indexed by I is safe. And the information we had was nothing. So the SMT said, I cannot prove this property. It said not. And what we did then is we added a runtime check, right? So in the logic, refinement type said that I know that this condition holds, so under this condition, prove exactly the same thing. And SMT says, yes, I can prove that. So we saw that verification is case sensitive in the sense that it takes into account the conditions that it has. We saw that it's type-based. Like we saw that we can refine things inside structures like lists, and this is like very, very important feature. We saw that, so no, we didn't, kind of. But it is decidable in the sense that the formulas that we put in the logic needs to be decided by the SMT solver. And OK, and the question here is yes. Like it's like they are very, like these kind of formulas are enough to talk about safe indexing or division by 0. But then we saw that to talk about deeper properties like associativity, we need to do manual proofs. And these proofs are helped by these two features that we have that Liquid Haskell has, proof by logical evaluation that just unfolds the function and does step. And we also have this rewriting using SMT. We call it REST, the rewrite with. And for example, yes, it's a kind of new feature that we have. We use the rewrite with to tell it. And it has a nice theory behind that it's using like online termination to see that it's not like this rewriting process is not going to diverge. And another feature that I think is really important, it is that it is language integrated in the sense that it's called by the Haskell compiler, and it can use all the nice features that the Haskell compiler has, which means that I can use like this. I can use Copilot. I can use flight check mode. I can make it part of my development tool. It can run every time I run the developer. I can use it in the cloud testing when I release projects. And yes, so these are the main feature of Liquid Haskell, and they can be used for refinement type checkers. Like they are decidable, type-based, case-sensitive, highly automated by SMT, and they are integrated on languages. And with this, we can conclude, like I can conclude, that this makes refinement types a practical alternative to other verification tools. And in the next 10 minutes, we are going to see three other features of refinement types, if they are expressive, if they are general, and if they are sound. And so for expressiveness, again, if you stay in the light fragment of refinement types, it is very easy and very direct to encode things like sortedness, safe indexing. But also, like if you go in the deeper side, you can encode more interesting features. And one domain that we have, like I have worked enough, is this secure web applications. And I have to finish. OK, maybe I can skip. Yes, I will skip this part of expressiveness. But the idea is that there is a way to encode. Yes. OK, I skip this part. So what can be expressed? And the idea is, like, if you are a programmer, you can very easily use the light part of safe indexing. And if you want to do a PhD and you have a domain that you can use, you can spend a lot of time to try to encode things using like special features, maybe even like advance the tool. And you can encode domains in the refinement types. But like for the specific domains, if you want to be expressive, it is like usually it's open research problems. So let's see how general they are, refinement types. And we saw like Liquid Haskell, so they can be used definitely to verify properties in Haskell. But like this style of refinement types actually started from ML. And like when we ported refinement types from ML to Haskell, we had to address this laziness problem. So it was a very challenging part. And recently we ported them to Rust, and there the problem was like, how do you deal with memory management? And this like liquid Rust Flux is an active project. And then there is a group of EPFL with Conchad and all that have a group that is called have a project that is called Stainless. And like, if I understood correctly, they actually want to ship refinement types in Scala. So Stainless works, but they want to have like more smooth integration with the Scala compiler. And actually, in this POPL, like tomorrow, there is a paper that is using index types for WebAssembly. But indexes is, again, like a very lighter form of refinement types, and they use this indexing to remove runtime checks from WebAssembly. So there are many languages that use the refinement types, and all of them need some adjusting when you develop them. So yes, you can, like if you develop a refinement type system for a language, you have to carefully think what are the features of the languages. But there are many, many principles that are exactly the same, and they are general. And there is a nice tutorial on how to build refinement types for your language. So there is no theory, but there is like, OK, I have this language, it has this feature. Let me explain you what steps you need so that you build it. OK, and I am going to the last question, the last feature, if refinement types are sound. And here, like, we go back, what is the soundness of a type system? And we say that the type system is sound when it only accepts programs that cannot get stuck. And usually we use this syntax to encode this and say that if an expression has a type T and it evaluates to another expression E, then either E is a value or it takes a step. And this is the standard definition of saying that the type checking that is defined is sound. OK, so what we did in the paper that will be presented on Friday is we say, OK, we have a definition of soundness. We have liquid Haskell as a prover to do deep properties. So let's encode soundness as a liquid Haskell refinement type, as we used refinement types to encode associativity. And like here again, we extending a little, we had to do some novelties, like we defined evaluation is a property, but like these two are quite the same. It says for every expression is 0, for every type T, if it holds the property that E0 has type T, then for every expression E, if it holds the property that E0 evaluates to E, then either, and this is very cool because this is either Haskell's either to encode or, either E is a value or there exists another type that it steps to. And this is a refinement type, and the proof, yes. So has type, models refinement type checker, and then evals to models evaluation. And we proved this property in liquid Haskell in about 10K lines of code. And this is the proof. It is by induction on the evaluation, and it is like the standard property. The base case, I am calling progress. In the inductive case, I'm calling soundness on the preservation theorem. And I mean, OK, like it, so actually this is the top level proof, and it's quite cool because it uses Haskell's features to prove this property. And again, this is going to be presented on Friday. And with this one could conclude that refinement types are sound. Usually I expect some objections. let me, OK, give me 2 more minutes, I guess, to finish. But Yeah, I mean, obviously, yes, there are some problems. And one problem is that the proof happened on the model of a refinement type checker. Like, this is a theoretical problem. And an actual problem is that if you go to the repo of Liquid Haskell or like Stainless or other program verifiers, you're going to see that they have soundness bugs, where soundness bug means that the program is accepted while it violates the specification. And this is against like the soundness property. And again, the 5 soundness bugs is like a lot compared to more sound developments, like Coq, for example, that is proven to be sound. Again, like there is about 1 or less soundness bug per year. And so the reason is that Liquid Haskell implements some core that is formalized. Its model is formalized. But it also has many, many features that are not formalized. And also, like, the implementation is huge. So we call this trusted code base. And we trust that this actually implements whatever is proved in the model, right? And so this picture is quite different in Coq, for example, or other theorem provers that are designed to be sound. So Coq has a tiny trusted code base that implements the calculus of inductive constructions. That is a theory that reduces to set theory. We know that set theory is consistent, which means that we know that calculus of inductive construction also is like sound. And the only missing part is this like trusted code base. And there is a nice project that is actually trying to prove the meta theory of this trusted code base to prove that Coq is actually very, very sound. And this 1 bug per year hopefully will reduce to 0. And so, like, the goal that I see in this, like, the theoretical goal in this development of refinement types is that we can close the gap. We can use this, like, practical interface of refinement types, and we can actually have our programs checked by Coq at the end. And there is a big gap because there is a lot of features that aim for automation and practicality in refinement types. And there are ways to do that. Like, for example, last year at ICFP, there was a very nice paper. It's called Explicit Refinement Types that could serve as a tool to close this gap. Or then we can develop a CIC-like theory that can actually be proven consistent of refinement types. And this goal would lead to a tool that is more practical from the user side and also like sound from the foundational side. But for now, I'm going to have a crush in the soundness part, and I'm going to thank you for your attention. There was a question there that I stopped. Yes. OK.
Nikki, wonderful stuff. Are you familiar with this, very old-fashioned prover called ACL2?
Yes.
If you are familiar with it, could you comment on how the fundamentals of your prover differ from ACL2?
It doesn't have this property that you can refine elements inside the structures, right?
I actually know very little.
Yes, I think this is one of the key, it's like refinement types combined in DEAs from ACL2, from runtime checks, from many things. But I think one difference is this, that the refinements go in the types, and the types can be inside containers, inside functions, inside everything. And then using the typing rules, it's more easy to deconstruct what you are actually sending to the solver.
I was curious about, so you showed that undefined can inhabit any refinement. So I was curious about how that factors into your soundness results. Do you have to make some statements about how there's no undefined in your programs, or?
Yes. In my theoretic soundness result, yes, undefined is not in the in a calculus that you are going to prove sound, you cannot have undefined because it's actually no, undefined is implemented in Haskell as undefined is equal to undefined, so this will not pass my termination checker.
Okay. But it is still usable in Liquid Haskell. Like, so this is an exception to the termination checking, or?
So no, because termination checker runs per module. Undefined is defined in Prelude, and we haven't like a module that defines undefined, it will fail the termination checker. But when you import things from Prelude, like Prelude doesn't run undefined. Do I answer the question?
Yes, yes. Okay.
I was curious how refinement types like interact with optimization. For example, we had to rewrite reverse to be inefficient. Do they work with like an optimized version of reverse, or do we have to like have the naive version?
It depends on what properties you want to prove. If you have an optimized version of reverse and you want to prove theorems about it, I think it will be more difficult to prove theorems. But there is actually a proof in, there is a paper, Theorem Proving for All, that proves that the reverse and its optimized version are actually equivalent. So yes.
Okay, so if you have like some optimized version, you typically have to like rewrite it in like a less optimized version and prove equivalence?
Yes.
Okay.
I think we're out of time. It's already 45, so let's take the next of the question after and thank Nikki. And Nikki's sticking around to be in the panel, and I invite the other panelists to also join us on stage. Okay, everybody.
you. I hope you all had a good lunch. We're going to start off with a more technical talk from Alejandro Russo from Chalmers University and DePella.
Yep.
And he's going to tell us about information flow and the GDPR.
That's right. Thank you. Thanks, everyone. All right, yeah. So in this talk, I'm going to talk about like some motivation about the research area that I've been doing, a new motivation I found in a research area that I've been doing for 10, 15 years. And I hope to transmit the enthusiasm to you as well. And then we will go a little bit more technical in that area. And then we will wrap up with some reflections that I have about doing research in PL that perhaps it will help you out in your own research in the future. So what was my research? My research was mainly focused on confinement. What does it mean, confinement? Today we have like a user interacting with computer system. The box is a computer system. And sorry, that system can store data in persistent storage, and it has internet connection because it's 2024, right? So we have internet connection from where we always take resources from. Okay? This is pretty similar. You know, you can almost any system you can map it to this architecture. So the user will provide data. Sometimes it will provide personal data, private data, and it can go to the persistent storage. That's fine. But then does it leak on the internet? That's the personal data that you provide to the computers goes to places where you don't know. And that's the main challenge. How do we build systems that confine sensitive data? Well, confine means like I know it remains within the boundaries of the system, and it doesn't go to anywhere that I'm not giving authorization to go. All right, so this is the outline of the talk. We went through, we will go through motivation, research. These are the more technical parts. And then impact, communities, and general learning. The part that you see on below is especially tuned for PLMW. The others is more like more technical conference style of talk. All right, motivation. Today, we are putting a lot of information into computers, a lot of personal information, and that needs to be taken care in a special way. And in Europe, we have what is called GDPR, the General Data Protection Regulation, which dictates how computer systems should handle your personal information, giving you as a user rights on your own, on the information that you generate. Okay, this regulation is from 2018. And how well are we doing following it? So yeah, so there you can see that there is 2.77 billion euros in fines. Computer systems that do not follow GDPR. GDPR is a monster. I mean, it's really a big regulation. So yeah, but what I want you to see is like the number of fines and the numbers of amount of money being paid is accumulating quite quickly. Okay. Right. So how do we deal with this with GDPR in a way? How we build software in a way that can follow many of the principles of GDPR. The regulation is structured in principles, and computer systems should follow those principles. Okay? GDPR has as well some part which is social and legal, like you need to have in your company someone that is called data protection officer. We will not focus on that. We will focus on principles that we can enforce in a technical way. And here you have many of the principles. We will go through them. But these are widely applicable. So these are one of the main principles of GDPR, and the ones that I believe can be automatically enforced. Okay? I have no answer to how to enforce them in an automatic way, but I give you an intuition why I think my research could help into that. Okay? Yeah. And if you look into all the fines, you will see that they violate most of one, two, or three of these principles. And you will say, well, but you come from Sweden, right? So you care about GDPR because you're European. I don't care about that, right? But then in China we have now PIPL, which is similar to some extent to GDPR, inspired by GDPR. We have in Brazil one that is pretty much a copy and paste of GDPR. And then we have the California Consumer Privacy Act, which is also inspired by GDPR. So GDPR is leading the way with these principles of how the future of computer system should handle personal data. Okay? Right, and my insight is the following. That's, I mean, I'll be hand wavy, but you know, GDPR, those principles, can be seen as controlling how information moves in the system, plus doing what is called safeguard data disclosure. Safeguard data disclosure means like when you publish data, you are not putting the privacy of anyone at risk. Okay? So let's go through the different ones. For example, right to consent or withdraw. Right to consent means like when you collect information, a system collects information that is personal to you, it needs to ask for your consent. You need to agree with that. And at any point, you can withdraw that consent and say, I don't give you more permission to collect my personal data. This is about switching on and off an information flow. Information flow from here to there, and then you cut it. Transparency and auditing is about you need to show in your system how handle personal data, where the personal data of the users go. And you need to be able to show that. And that's about tracking where data has been sent. No identifiable data disclosure means what I just said before, that when you publish data about a set of users, for example, you should not put the privacy of anyone at risk. Purpose means when you collect data, you can only process it for the purpose that you give consent to. That information cannot be used for anything else, right? Except for the thing that you agree upon. And that means for information flow, it's like it only will go to the part of the system that you give consent to process it. It should not go anywhere else. Data portability means you have the right to ask information about you and get that information in a machine-readable manner. But for doing that, you need to know where your data is. So you need to know where the data that you have right to the system has been propagated, where it has been flowed, because you need to collect it and then give it to the user. Data minimization means you only ask the data, the minimum data that is necessary for the purpose to process the data. And here you can see, from a system perspective, you can see this is my output. If we go back in the processing pipeline, these are the inputs that I need. I need to reason how the outputs are dependent on the inputs. And processing control means at any time you can say that you want to stop the processing of your personal data, and you have the right to do so. Right? So your data is flowing in the system, and at some point you need to cut it. Okay? As you can see, it's all about locating where the data is and how it's flowing within the system. I believe that those principles can be all addressed with the information flow, a research called as information flow control. And safeguard data disclosure with a different technique called differential privacy. Okay? These are my insights about how I believe that this can be solved. It has not been done, has not been explored, but I believe so that there is a lot of potential there. All right. So now let me show you information flow control, which is like reasoning how data moves and enabling data moves in one way with another and restricting that data moves in one way or another. Okay? And for that, we got to my research. Remember, that was my problem, right? So, yeah. One thing that you should be aware of is like enforcing confinement is not about giving access to the data or not. It's not like I need to give access to the private information or not. It's about once I give you access to that data, it shouldn't spread widely. I need to confine it. Okay? It's about how you handle the information. It's not if I give you access or not. And it's known as information flow control or mandatory access control, depending if you come from the PL community or the operating system community. Right? And I have discussion with people in the post community, and one say that the other one is not general, and one, they fight which one's right. I will not get into that. Yeah. So this idea of tracking how information propagates in your programs has been explored by many researchers, and there are even compilers like Chief that you write Java programs and you can reason how data moves within the program. Okay? And making sure that sensitive information doesn't go to unwanted places. We have Paragon, which is from Chalmers. Then we have GSFlow, which is from Chalmers, but it's for JavaScript. Paragon is also for Java, sorry. And Cowl, which is from JavaScript, and the list go on and go on. People have done it for compilers, for interpreters, for operating systems. A different level of abstraction, how to track information, how information moves. In the whole ecosystem that we have here, we have Haskell. That plays a unique role, which is like you can do information flow or tracking how information moves by just providing a library. And you say, well, why is that important? Because for the operating systems, the compilers or the interpreters you see on the screen, you need to modify the compiler. You need to modify the interpreter. You need to modify the operating system. And that's a lot of work. Right? In a pure functional language, we can provide it as a library, which is great. But why this works in Haskell and it doesn't work in OCaml, for example? Nothing wrong with OCaml, but why it doesn't work with OCaml? And it's because Haskell has a type system and has decided to have a type system that partition side-effect-free computations from side-effectful ones. Right? So you have side-effect code. Side-effect code is intrinsically confined. You know that the information you put in the input of the function goes to the output, and it doesn't go anywhere else. In the side-effectful code, you can do whatever you want, right? So it's like I get an input, my function gets an input, and then that information can go over the network, right? And Haskell has the I/O monad that says, here it's indicating you, it's signaling here there might be some side effects. Be careful, right? That's right. So let's see a concrete example about this. I'm Alice, I'm writing a password manager, and I want to refrain users to pick commonly used password, like 1, 2, 3, 4. Alice is very lazy, doesn't want to write code. So she looks for some code that is provided by Bob, a ninja. Right? He's a ninja programmer. And then what do? Alice will use that code. So when the users provide the passwords, it will go to Bob, to the code that Bob wrote, and go back to Alice and say, yes, it's a commonly used password or it's not a commonly used password. The problem is you don't know if Bob code will make a copy of the password and send it to the server. Right? How can we show that that's not the case? All right, now let's go for some challenge. Bob provides the following type from the common function, which is the function that checks if your password is commonly used or not. This is the type. So I want to see how many of you will use that function. If you are Alice. 1, 2, 3. It's everyone very careful now. Right. This is a pure function, so it's strictly confined. So you know that the password doesn't go anywhere. You can use it. But the problem is you need to hard code the dictionary of commonly used passwords. Okay? It needs to be coded in that function. Now, if common has this type, a string to IO bool, who will use it? Raise your hand. Nobody, right? Why? Because it has the power to do everything. You get a string, and then it can do whatever it wants. Right. So now I tell you, well, then the problem is you are doing a lot of things with the IO monad. You have the power to do many things. I said, well, actually, the code has now the type safe IO that has one side effect, which is fetching dictionary updates. That's it. It cannot do anything else. Will you use that function? Do you use it? A couple of things. Say no. All right. The answer is even in the request of the dictionary update, you can encode the password information. Right? So no. All right. So then what do we do then? Right? And what I'm going to show you here is a functional pair I wrote in 2015, where I found it the simplest way to present information flow control. and how to solve the problem, the dilemma of Alice and Bob in the password management. So we are going to make Bob sure that use some security types, and by Bob using those types, I can be sure that the information is not being leaked, while the Bob code can still fetch dictionary updates. Okay? We're going to provide a family of monads. Ideally, it's like you start with a super liberal monad. As soon as you read a secret, now the monad only will perform side effects which do not leak information. Okay? Right. So, and we, I'm not going to show you all of that, but in a functional pair, you can see how to deal with very advanced. These are, from the information flow perspective, these are very advanced features. We will do everything in 200 lines of code, and we will use Haskell 98. Probably nobody was, many of you were not born by then. And we will use two type classes. Two extensions, multi-parameter type classes, and save Haskell. And then we go to the save Haskell part in a bit. All right. So the first thing, this is the introduction to information flow control in maybe 10 minutes. It's like we start choosing a security level. A security level, it represents how sensitive information is. And I'm going to accommodate all the security levels in a lattice. It's not necessary, but it's convenient. We put it in a lattice. And the important thing is like information can flow from data with a security level from the lower to the highest part of the lattice. All right? So I'm going to give you an example. This is the thing you need to remember. If I got two labels, information with label L can flow into entities of label L prime if L is below in the lattice than L prime. Okay? So for this talk, we are going to choose a 2-point lattice. I have only 2 points in the lattice. One is L of low for public and H or high for secret. And low flows into high, but not the other way around. Okay? So the lattice is telling us the policy about how information is allowed to flow. So, okay, how do we encode this in Haskell? Every point in the lattice, we make it an abstract data type. And how do we encode the order relationship? We have a type class that has instances, all the allowed ones, and there is only one missing, which is going from high to low. Okay, so the compiler knows about the security levels and what information can go from L to H. All right, now that we have security levels, how do we put labels in data? Right? We have another abstract data type called label, LA, that says A has label L. Example, a credit card is a secret integer. We'll have type label HInt. A weather report is a public string, which has a label L attached to it. Okay? Great. We can classify the sensitivity of the information. We can attach it to data. How do we build computations now that make sure that we don't leak sensitive information? And for that, we have an extra abstract data type called Mac, LA. And essentially, it's a wrapper of I/O. So Mac LA underneath will have I/O actions that are guaranteed to not leak information. But we will go in a second how we will build that. And the way that you think about this is like Mac LA is a side-effectful computation that handles all information at level L and produces a result A of label L as well. Example. We have public, it's a Mac L string. It means like it's a computation that does things with public data, only with public data, and it produces a public integer. Secret, handle all sensitive information, and produce a secret string. Okay. Now we have a family of monads. Monads are indexed by the security level, so we have Mac L, Mac H. Okay. One dealing with public data, one dealing with secret data. And then as you can see, it's just a wrapper on I/O. You have the run function that just gives you the I/O actions underneath. That run function is not going to be used by Bob, the developer. It's going to be used by Alice. Right? Bob, the developer, we will see in a second, will only use the interface for Mac. Right. Mac comes from mandatory access control. And how can we build secure computation for that? And for that, I'm going to take some principle from operating system research from '73, where not even I was born. So by transitivity, none of you were born. So Mac LH, this principle says the following. In the abstract sense, a computation can read and write data. Right? If I read data, that data has some label, LRead. It's okay for that data to flow into the computation, which has label L, if LRead is less than, equal than L. Okay? This is called the no-read-up principle. A computation is secure if you are at a certain level, you can only read things that are less sensitive than you. Now, if you write into a sink, that sink is also labeled with LWrite. And now the information needs to move from the computation into the sink. Right? So now I need to check that L is less equal than LWrite. This is known as the no write down. A computation is secure if I'm at a certain level and I only write above me, never below. If you are a secret computation, you cannot write into a public file because you might be leaking sensitive information. All right. Now, let me give you an example of a very simple source and sink of information, which are Haskell expressions. Right? Label LA, you can think that as a source or sink of information, where the A is the information is expression of type A. We will have two functions, label and unlabel. The first one, what it does, you take an expression of type A and you create a label value. You put it inside a label data type. Since we are creating is like writing. It's like, and I need to allocate a empty piece of memory and then write something into it. Right? So therefore, I have a MacL computation creating something of type label L create A. I need to write, if I'm MacL, I need to write things above me. That's the no write down policy as a type constraint. The unlabel is the reading. You have a label source with LRead, and you will expose it to the computation. Therefore, to flow into the computation, it needs to be the case that LRead flows into L. That's the no read-up policy. So these two principles of operating system are captured as type constraints. And this is the most simple example, but if you tweak A here, you specialize it a little bit, you can have references and M bars. You can have different abstractions which are aware about information flow control. You can have a Mac computation that does read and write references in a secure way. All right. So let's go back to the example, Bob. Now I said to Bob, this is the type I want for your for the routine to check commonly used password. I want you to take a secret string, and now as a result, I will get a MacL computation. This is the MacL computation that deals with public information. This is the one that fetches dictionary updates. And as a result of that, after that, I get a MacH computation, which checks if the password is inside the thing that I have just fetched. Alice, what it does, asks the user, what is your password? And I will wrap it in a label H string type within a MacL computation. And now you can see the, do I have this? Yeah, no. You see the label password, now it's given to the piece of code of Bob. And I know that now it's confined. Okay? All right. You run it, you get the MacH, and you run it again. All right, so I give you a super brief version about the security libraries of information flow control. but there are a bunch of different versions of it. I show you Mac, which is a static enforced with using types, but then you have dynamic ones, LIO, or a mixture of these two. So there's a bunch of literature if you're really interested in this area. Going back to GDPR, now that you know information flow control, right? Now imagine that instead of having security labels like L and H, very simple ones, now you have a label that says who this information belongs to. Okay? And now we can track, you know, if I combine information from Ale and Leonidas, it gets combined. Now I say this information belongs to both Ale and Leonidas. If I want to do something with that, I need to ask the consent of Leonidas and Alejandro. Okay? So my idea is to create computations, this kind of computational unit you can see here. You have three parts. You live inside the computation. That's the area A, where we will use information flow control to keep track who owns which information. Then when you go to area B, which is like you want to store it, then based on the label who this information belongs to, you will choose certain cryptographic keys to write it in an external store. And then when you want to disclose information, the area C, you will use these data disclosure techniques like differential privacy. So this is a project that I'm going to carry out in the next 4 or 5 years, and this is kind of the concept that I'm playing with. And I have a little bit of something to show you here, which is like Haskell last year. We published a paper that started kind of making a reality this kind of model I'm showing you. All right. Right. So now this was the most technical part. So now I will try to. This is PLMW. I'll kind of go through some of my research, the impact of what I mean by impact in my research, communities, and general learning. So hopefully, if you decide to jump in this area or in the area that you're working on, maybe what I'm going to tell you might resonate or might help you out in the future. All right. So what do I mean by impact? When you do research, your impact is like, you know, it can go make the world a better place, solving hard problems, right? But that's very cheesy. Usually what it means is like, I'm in my bubble, let me alone, right, to do with the things that I like. But at some point, you need to go out from your bubble. And how do you get out? You start with what I call, these are my own invention, so it's not brilliant. It's just like something I came up with. But you know, level 0, publication and citations. When you do your PhD, the way to have some impact is publication and citations. That's the way to you start getting out of your bubble. Then the next level, every level is exponentially hard to achieve, right? So you know, it's not linear. Level 1 is like your research is used by others, right? And I found that writing code and making code available is a very convenient way for others to take on my research. And the library I show you, for example, I took a snapshot. It was like download 2,700 times by December, right? It's some modest impact, I would say. Okay, in the Haskell community, I don't know, what is the most used package in Haskell? And then, so I guess like this kind of issue during your studies, you can address it, or you can start planning addressing it. And then level 2 is like adoption of your ideas in production. This is like taking your idea into the market. And that's very hard. So I created a company 3 years ago to try to take some of my PL research into industry, right? And after 3 years, we don't have a customer yet, hopefully this year. So then you understand how hard it is. Right. Cool. And then you can make the world a better place, right? So this is kind of the stair of impact. All right. So now, one thing I want to encourage you to do is to publish across different research community. So I consider myself like in the middle of these things. At some point, I was confused. I was like, you know, I'm a security guy, then I was a functional programmer, operating system by chance, and But then I understood that I'm non-binary, so like I'm not identified with any of S3. So like, and every community. So then we in PL, we have the unique chance to publish in different communities. It doesn't happen with many areas, research areas. So take that advantage. But be aware that each community has different, they focus on different things. What I'm saying now is not sufficient to publish there, but it's very necessary, okay? For example, in functional programming, language design is very important, right? Then in security proofs are very important. In operating system, evaluation is very important. And you say, well, Alejandro, why are you so sure about that, about these kind of things? Well, I went into the source of all truths, which is the rejection reviews of your papers, right? So, language design. We got this for one PL conference. The proof about the language described in section 2 just don't say much about the real world language. So the language design, the language was unsexy, was not real. Soundness. In the end, they obtain essentially the same semantic proof as in 6. They're just blowing smoke and not a contribution. All right? They really went and looked into the proof. Okay? Evaluation. The bulk of the material is fairly abstract and esoteric. It relates almost no experience in actually using the language to build substantial or realistic applications. Okay? So, yeah. So then you understand when you choose a community, try to see what is the main focus that they have to understand how do you get your PL research through them. All right. So now some general learnings that it might help you out in your career. So on the first one is, recently because of the company, I've been doing some business training, right? And at some point we were really want a strategy, right? So we faculties at the university, we talk about what is the strategy of the department in the next 5 years, 10 years, or what is the vision of the whole university in 5, 10 years, and things like that. And companies do the same thing. And this is a business study where it shows through many years what is the impact of a strategy in the success of a company. And you have here, this is like something that is happening in your industry that gives you success. This is the strategy. But then look at the color on the most right-hand side. It says other factors. Things that are not part of the strategy. You should have a strategy, yes, but it's not the only thing. That's my message. When I read this, I said, this is bollocks. I mean, doesn't make sense. And then I reflect on my career since I become a professor. I had a strategy. I go to Chalmers to study. In 2004, I got rejected, so I was not good enough to get into Chalmers. 2005, I met Andres Abelfeld, who was my advisor during my PhD studies, that it's just in an event. I met him, and he was looking for a PhD student and offered me a position on the spot. But the reason for that he offered me the position is that because he hired a person to do the PhD, and 2 weeks before starting, that person resigned. So I got in. Right. My strategy, I should become a faculty at Chalmers. It's a great place, great PL, right? 2010, there was an opening for assistant professorship. I decided not to apply because I was having this issue, I'm more a security guy than a functional programmer. And then the day before the deadline, I came out of the room and I came across Koen Klassen, who is a functional programmer. And he told me, are you applying, Alejandro? I said, no. It's I'm not a functional. No, you are, blah, blah. Convinced me the whole night writing the proposal. I sent it in. I didn't win. There were four candidates in the final. The first one was Dimitro Vitivinois, who was one of my co-authors, great guy. The second was myself. Dimitros decided, no, I'm not going to Chalmers. Then I got the position. Right? So, going back, It's not that bollocks. So my strategy now is to have a strategy, but also be exposure to lag. What does it mean to be exposure to lag? Try to talk to as many people as you can. Try to network in conferences as much as you can, because you never know where the next lag will come. You know, where the lag is going to come from. Okay? Right. So, and the second learning, for me, it's like, you know, as a PhD student, you need to be ready for failure. You need to be ready for failure because, you know, you will fail, as I show you all my reviews. And for example, you know, I got in 2016, there was a very competitive grant for, in Sweden, for, you know, research leaders across all disciplines. There were 225 applications, and there were, I was number 22nd, and they only granted 20. Huh? So, yeah, I was very down by then. Then recently, about 2 years ago, I was in the ERC Consolidator grant. This is one of the most prestigious grants in Europe. There were like 2,600 proposals, only 300 in the interview phase. I was in the interview phase, and then didn't get it. So, what I do when I have this kind of situation, or you know, what are the things that since 2022 I've been doing when I have bad situations? I'm originally from Argentina. What is the most famous sport in Argentina? Football, that's right. So now I took inspiration about this guy, right? Which you might know, Messi. He lost 4 finals, 1 World Cup and 3 American Cup. And he's the most talented guy in football in the whole history. Yeah. All right. I'm biased. I'm biased. But the guy keep pushing. And finally, he made it in 2022. Okay? So the message is like, you know, if the guy has the most talent in the world and keep trying, you can also keep trying. Okay? So, I have show you, to wrap up, I have shown you, you know, how I believe data privacy regulations can be tracked or addressed from a foundational way using information flow control. I have shown you information flow control from the point of view of a security library in Haskell, and I show you the core principles of the research area. And as I said before, PL has a tremendous opportunity to make impact across communities. So take advantage of that, or keep that in mind when you do your studies. And hopefully, you know, when you finish and you achieve great success, we will feel like raising your academic World Cup. Thank you very much.
All right, we have a little more than 5 minutes for questions, if people have any.
Hi, thanks for the talk. I was wondering whether, you know, in your type system, you could provide like safety against like timing attacks and sort of other side channels.
Right, timing is, no, the short answer is no, right? And we could be yes, but you need to be very, very conservative, right? So timing is very hard to deal with. Yeah. So these simple kind of libraries are not well prepared for side channels like timing, right? We will be interested to see if you can do something with that. Yeah.
Hi, I have a question about your Max library and you showing the directions of like data flow. I was thinking about computations which like lose data. So like, for example, if you're taking a hash of a password, have you got some way of like encoding into the library that the data is now safe to become public in a type safe way?
Yeah, what you can do is like when you define what is called the non-proper morphisms of the MAC monad, you can say, well, there is one that say hash. It goes from label H string to label L string, right? but then you give it as a part of the trusting computing base. It's something that you trust that that type signature is correct.
And you have to verify that separately.
That's right. That's right.
Thank you. Very interesting talk. I had two questions, one of which you might have already covered and I didn't notice was, in the Haskell examples, presumably you have to disable things like unsafe perform IO.
Thanks a lot. Yeah, I forgot about that. Yeah. Now, let me ask you this. Yeah. Sorry, I didn't deliver on my promise that I will explain you about Safe Haskell. Safe Haskell, Haskell has extensions, which in the name of performance, you really need them. They break type safety and module encapsulation. Safe Haskell is an extension that disables those extensions that break type safety and module encapsulation. So then you can have guarantees that you can trust your types, essentially. Yeah.
And then the other question I had was actually more to do with when you mentioned some tools that work with JavaScript. I'm aware that in JavaScript you have quite pervasively things that essentially amount to some form of metaprogramming, in that I can interpret arbitrary strings as code and various things. When these tools are written for JavaScript, do they essentially somehow just disable those features, or do they do something clever to track this information?
So, yeah, I can tell you what I've been working. When we work on information flow on JavaScript, it was a COWL system. We didn't want to mess with the JavaScript semantics because of all these, exotic features, right? So what we did instead is like we look. The browser is already provide isolation compartments, like a browsing context or empty JavaScript context, and we kind of put a boundary around that, and then we control what goes out, goes in, right? It's more coarse-grained, but that was the best way we found to I don't care what you do with JavaScript, these fancy features, I just control what gets in and gets out. As soon as something secret gets in, everything gets tainted, right? And then the communication might get restricted to the outside world. Yeah.
Thanks for the talk. You mentioned that you'd produced a library that had quite a lot of success. Obviously, there's lots of features, lots of prerequisites for this. So it has to be well designed, have a nice API. Maybe you publish a paper that provides the theory, but you can do all of these things and it not take off. You could have a great system that's brilliant user interface, solid foundation that's been published, but no one uses it. So is there anything you did outside of these design factors that encouraged it to be picked up by the applied community, or was that another luck factor?
Right. So I would say that I don't know if 2000 something will take off in the information flow community. I don't know, but maybe. But I would say no. We didn't do anything. We just publish the paper, write in the code. We focus a lot on simplicity. I think simplicity is key, right? So sometimes you need to do some. If you look. I remember my first paper, that was super complicated because, as a PhD student, I want to throw all this, I want to demonstrate that I can handle a lot of complicated stuff. But the more I advance in my career, the more maybe my mind is reducing capacity, but, the more simple I become. And I think that's kind of one thing that we did consciously with LIO and Mac and the work in JavaScript, COW, to be as simple as possible. And that's got some traction. Yeah.
Okay, thanks.
All right, I think we're going to have to cut it off there. Let's thank Ale again.
Thank you very much.
Sam Froelich from University of Bristol. She's going to talk to us about collaboration.
on? Is this on? Am I mic'd? Yeah. Hello everyone, I am Sam, she, her, and today I'll be telling you guys about research collaborations, why you want them, how you start them, and how you make them successful. Oh, you know what guys? Actually this feels wrong. I feel like I can't give a talk about collaboration on my own. Can someone come up and help me? Oh gosh, Harry! Oh, thank God. We've collaborated before. I think this is really going to work out. Harry, introduce yourself.
Gotta change the slide.
Oh, yeah. Oh, much better.
Hi, everyone. My name is Harry. My pronouns are he, him. At last year's ICFP, Sam and I gave a tag team talk, and people seemed to like it. And my friend Joe, who's sitting in the audience now, texted me and said, you know, this is great. You guys should do a talk on collaboration. Wouldn't that be funny? And I turned to Leo, who was standing next to me, and I said, look at this funny text from Joe. And he said, wait, I'm in charge of PLMW at POPL'. You're doing that. Oh, okay.
And now we're doing it.
Now we're doing it.
Just a little note on questions. Since it's a two-people one, just hold them till the end. But we've left plenty of time for them.
Thank you. Okay, so let's get started. Why should you think about collaborating in your research? I think the short version is that research is fundamentally collaborative. It's sort of hard to do research without collaborating, and collaboration is what makes the whole research community work. But I think there's some more specific reasons that you should consider collaboration. And so let's look at those now. First, collaboration brings more ideas. And speaking of more ideas, throughout this talk, you're going to see quotes from folks in the community who do a lot of collaboration that we decided to collaborate with and ask for their input. So the first quote is from Nadia Polikarpova, and she says that the research community is a distributed system made up of very small brains. And while each of us individually can't do much, communication and collaboration is how ideas are born. And that's certainly been true in my research. I've had a couple of ideas on my own, but by far the vast majority of the things that I've done have been in collaboration with others. That's just kind of how the ideas come to pass. Next, important expertise. So I have my things that I'm good at. I do property-based testing, and I think I know a lot about that. But there's plenty of things in PL and otherwise that I don't know about. I'm starting a project soon that's going to have some things to do with program synthesis. And rather than try to teach myself how to do program synthesis from scratch, I'm going to collaborate with folks who know it better and bring that expertise in so that I can be as effective as possible on that project. Next is new perspectives. So when I started my PhD, I had mostly a very pure PL perspective on the work that I was doing. But I got to a point where I wasn't sure what to do next. There were a lot of options available, and I kind of figured there were some options that I wasn't even seeing. And I didn't know how to move forward, how to decide what to do next. But a human-computer interaction professor came to Penn, Andrew Head, and in collaborating with him, I was able to borrow his perspective to bring some human-computer interaction into my research, and it's totally changed the way that I look at research and the way that I approach the work that I do. And none of that would have happened if I hadn't tried to collaborate. Next is maybe obvious, but important to state. 2 heads are better than 1. Simon Peyton-Jones says that if he just sits on his own, he goes round in circles. And I think that's true of me as well. You can sort of sit in your home alone and try to come up with the solution to this hard problem that's been vexing you, but you really often won't find the solution until you go and talk to someone who can help you reason through it. And finally, collaboration is really fun. Sam and I have been collaborating for the last year and a bit, and I visited Bristol, Sam visited Philly. It's been really great and fun to do collaborative research, certainly more fun than doing it alone. The big idea here is that you basically just can't do research effectively alone. Collaboration multiplies your effectiveness, makes a research community stronger, And everyone we spoke to for help with this said that collaboration's really a key part and you can't avoid it. And to illustrate, this is a new slide. To illustrate, my advisor, Benjamin Pierce, we had a 60th birthday celebration for him over the weekend. And he had this slide in a slide deck that he put up. This is the 2 books and 3 papers that he's written on his own in his whole career. And then the 113 papers in the 4 books he's written with collaborators. And I did some math, and it was at least 60 collaborators in total. So I think that's as good a reason as any to try to make collaboration part of what you do. So now Sam is going to tell you how to get started.
Yeah, hopefully we've convinced you that you do want a collaboration. So how do you get one? I thought I'd start by telling you our story. So let's take you back all the way to the student research competition at ICFP 2021. Harry submitted this poster to the competition, which is a really good idea. Submitting a poster to the student research competition is a great way to get feedback, develop an idea, and find a collaborator. And because I was working on an overlapping project, I went along to his presentation and really enjoyed it with my collaborators. Harry then emailed us to thank us for coming. That is something you can just do. You can just email someone. That is perfectly okay. And here's the email, because I thought I wanted to show you some things that Harry did well. So the first thing he did well is CC his supervisor. Maybe if you're a PhD student, you're less well known. It adds a bit of legitimacy to CC your supervisor, especially if your supervisor is Benjamin Pierce. Another thing I think Harry did really well is he was so enthusiastic. It's like, oh my gosh, thank you for coming. I really, enjoyed chatting to you guys. And he just really endeared himself to us by being super enthusiastic. His email was also extremely informative because he attached some of his code. So he said, oh, here's all my code. You can look at it if you want. His email was also specific. So he had 2 things that he wanted to get from us. He said, if possible, if you know, could you please answer these 2 specific questions? So it made it really easy to go, can we help you or can we not? There are 2 questions to answer. I then spent a week writing an email back. I didn't know if a week was way too long. I didn't know if I should be spending a week writing an email back. But the thing I should have done is acknowledged Harry's email. I should not have left him hanging for a week. So some logistics on emails. Acknowledge your emails. If someone sends you something really cool like this, say, oh, thank you for this. I'll take a look at it in the next week. And then he's not left like, is she looking at it? I don't know. Another tip is don't use BCC. So this is something I fell foul of when we were asking for our collaborations for this talk. I BCC'd everyone. Sometimes that can send your email straight into someone's spam. So maybe we would have had more quotes if I hadn't done that. So don't use BCC. And finally, sign your emails. Say best Sam. I had an intern who didn't do this and sent an email, and the recipient thought that they'd press send before they'd finish their email, and there was more content for the email. But she thought that she'd finished the email, and I had to be like, no, they think there's more. Send another email. So make sure you also sign your emails. Anyway, I spent a week, and here is an extract from the email that I sent back. So first of all, I took Harry's code and I annotated it with comments within an inch of its life. So I sent that code back and said, here are all of my thoughts. So I really engaged with what he'd sent me. I also returned your enthusiasm. I was equally enthusiastic, so I think that led to us wanting to collaborate together because we just shared the same enthusiasm. Because my email contained a lot of information, it had attachments, answers to his questions, all this stuff, I summarized what was in my email, so he knew exactly what he was getting from my response. I also decided to show a little bit of my personality, so his project was called Bidirectional Ungenerators, and I was like, hey, you should abbreviate that to bugs. It'll be cute.
There was a bug emoji in there and everything.
Yeah. We're still sad that we couldn't get that into the final paper. The next thing I did is I made sure I answered each point of the email he had sent to me. It seems like a simple thing, but it's commonly not done. Someone sends you 5 questions, and you only answer 1, and that's just sad. So make sure you've answered all parts of the question. So I think I even said, here's the answer to question 1. My answer to question 2 is, I don't know, but here's why. So I made sure I addressed all parts of his email. Finally, I shared some of my work because I was working on an overlapping project. I was like, you might be interested in what I've been up to. So we shared this enthusiasm. And then 2 years later, ICFP, last year, we were presenting our distinguished paper. And we hope that the rest of this presentation will help you get a successful collaboration too. Now that's just our story of how we ended up collaborating, but there are lots of other ways. And all these ways of starting a collaboration all share the same theme. It's all about showing interest in the work of others. And here's how you can get started with collaboration. Yeah, we took this yesterday. That's the Royal Albert Hall. The first thing you can do is introduce yourself. So before the break, turn to the person next to you, say hi, introduce yourself. During the break, go mingle. And I think we touched on mingling earlier, but there's all these little circles of nerds. Don't be afraid to join the circle. You're welcome in any circle. Just go quietly stand. Maybe they'll all turn to you and say, hey, introduce yourself. What's your name? Maybe they're just finishing off a conversation. You can wait for it to lull, and then they'll ask you to introduce yourself, or maybe you'll have some point to add to that conversation. So you can just introduce yourself. And if that's too scary, go join a circle with someone you already know. You now know me and Harry. Come join our circles. Another thing, you can get you don't have to introduce yourself. You can get yourself introduced. So ask your supervisor to introduce you to someone. It's their job. You can ask me or Harry. If we know someone, we'll do our best. And you could also ask another person in your research group as well. Or even better, something called matchmaking can happen. So ICFP was all the way in the States, so only a couple people in my research group went. I went around introducing myself to people, learning what they did, and I realized that someone was working on something very similar to a new PhD student in my group. And I said, oh, you should chat to her. I match-made them, and now they're collaborating, and I'm so proud. Another thing you can do is give talks. And again, this is something that you can just do. You can just email a university with a group that's working on the same sort of research as you and say, hey, can I give a talk on this? And if you don't have the funds to go in person, you could just do it virtually as well. It's great practice and a great way to get feedback. And one thing I want to point out is you don't need to present polished work. You can very much present unfinished work. Maybe someone in the audience has the answer. So my research group, we've got a seminar series, and we really do encourage unpolished, unfinished work. And if your research group does not have something like that, go start one. Another thing you can do is offer to help with projects. So there's a project that you really like, maybe you're using it in a different way than it was designed, or you think there's an extra feature. There's no harm in telling the original offer, hey, I'm doing this with your stuff. At minimum, they'll be really chuffed that someone's using their stuff. At maximum, they might go, oh, I never considered that. That's a really good idea. I would love to help you do that. And boom, you've got a collaborator. Finally, you can go to summer schools and make friends. So a summer school is a week or two long trip where a bunch of academics give courses on PL foundations. So common ones include OPLSS in Oregon, SPLV up in Scotland, MGS+, there's loads of them. And they're another great way, like PLMW, to make your cohort of PhD students make friends. I went to SPLV up in Scotland, and I had the best time. I made a bunch of friends with people at Chalmers, and that led to me going to visit them and give them a presentation. And also, when you have more friends, conferences are a lot less intimidating, because I look around a room and I go, oh gosh, thank God I know some of these people. I can go join those circles. And also, it meant I got to know the academics outside of my research group, which if I ever want to go back home to Scotland, you know, maybe that might help me get a job. I hope so. Who knows? When we asked our experts for their advice about starting collaborations, they had advice on both parts of it, finding that potential collaborator and turning that potential collaborator into a concrete collaborator. So the first quote's from John Hughes, and I think the key points here are, there's no substitute for actually meeting someone. That is the best way to work out if they're going to be the right collaborator for you. And the way you know if it's the right collaboration for you is if it's like a natural continuation of the conversation. I think he really puts that well. It shouldn't feel jarred. It should just feel natural. And then for turning that potential collaborator into a concrete one, my supervisor gave us this quote. I think the key takeaways here are, if you want something from someone, be upfront about that. Say, hey, I'd really love to do this with you. Are you able to do this? And the further in advance you tell them that, the more likely they are to be able to help, because they can think, oh, can I actually do this? Do I have the bandwidth? Can I make the bandwidth? Because they asked in advance. And that's all really helpful. And then when you're having that helpful chat with someone, make sure you spend 5-10 minutes at the end deciding with that person how you both want to proceed and agree that with them. Now, almost everything I've just said about starting a collaboration involves socialization. So remember to pace yourself, especially if you're an introvert. We're both introverts. Like, I came here and I did my first day and I was like, oh my God, I forgot how tiring this is. So just remember, you do not need to attend everything. You can skip a talk, you can skip a session, you can go have a nap in your room. That's especially understandable if you're jet lagged. I'm certainly very jet lagged from my trip from Bristol in England. You can also opt out of chatting to people on the breaks by just going and sitting quietly in the corner or quietly in a room just to recharge slightly. And there's no pressure to go networking every evening, going for dinner with people. If you really need to recharge yourself, just have a dinner by yourself in your room. And the key thing that I like to do is I like to have friends that drain my social battery less, and I alternate between hanging out with them and then networking. So I sort of bounce between those two things. I've got a rest place with my friends like Harry, but I can also go and network. You're not wasting opportunities by looking after yourself. You're actually making the most of them because you're ensuring that you've got the energy when it counts. So pace yourself. And now I'm going to tell you about recognizing Harry, what is this American rubbish?
I just thought that if we changed all the spellings to American spellings, I would feel more at home here in the UK.
This is just like the Great Spelling War of 2022.
Wait, I thought we don't talk about that.
Well, we're talking about it now. After all, it is a great example of a research conflict. Back in the spring of 2022, we realized we had to pick between proper British spelling and American rubbish. We decided to write our paper with British spelling, and that is that. So,
don't change the slide freely and not debate with me. Why should a tiny island across the sea regulate the use of Z?
Fine, I will rock, paper, scissors you for it. You ready? Rock, paper, scissors, shoot. Oh, see, I win. That was a dramatic retelling of how Harry and I settled which version of English to write our paper in.
Yeah, we actually did that. We rock, paper, scissors to figure out which spelling we should use, which in retrospect wasn't a great idea because that stuff actually matters, for example, if you're trying to splice that paper into your dissertation. So this is all goes to say you should communicate about these challenges and decide them rationally rather than just doing rock, paper, scissors.
But of course, other collaborations might have bigger differences than UK versus US spelling, and I'll go on to that now. So I've been lucky enough to work with a Japanese collaborator. This is me in Japan, and that's obviously got a much greater cultural difference. And I thought it'd be really useful to point out those differences because I really enjoyed learning about them. Those differences can lead to a really productive collaboration because you've got different perspectives, different points of view. And it's really important to be aware of these differences and approach them with an open mind and respect so that they don't turn into challenges. Okay? Yeah, thank you. So one of the differences is language. Harry and I may have joked about the difference between American and British spelling, but that's nothing compared to the difference between Japanese and English. They've got a whole different writing system, which I did know before this collaboration. But they also have sounds. Like we've got sounds in English that Japanese doesn't have. And that's something that I didn't know and was fascinated to learn about. I think I'm very lucky to natively speak the language that research is generally conducted in, because I can only imagine how hard it is to present or write a technical paper in another language. Heck, I have this streak on Duolingo, learning German. And while I'm very good at, ordering in a restaurant, I still need to ask native speakers to slow down and be patient which is why I'm more than happy to show any collaborator a similar respect and admiration. Another difference is holidays. So in the UK, Christmas is probably the biggest holiday. Like, the whole country just grinds to a halt. And this is a really important piece of information to share with your collaborator, especially if they don't celebrate it, because this means I can enjoy my holiday eating my mince pies, and they're not left waiting for me. So the UK-US example of this unshared holiday is Thanksgiving. So I don't celebrate Thanksgiving, but I understand it's a really important holiday in the US. So of course, I was more than happy for Harry to take that week off, and we arranged our workloads accordingly. One thing I noticed, a main difference between England and Japan is they've got different work cultures. And the two main things I noticed is firstly, respect is shown differently. So in the UK, I might be busy mates with my supervisor, and being cheeky to a senior person can be seen as charming and a sign of respect, because being able to joke with them shows that you respect them. I got the impression in Japan that respect was shown more traditionally, by being a willing and diligent student working for a supportive mentor. More like a knight-squire relationship as opposed to the parental one that can occur in the UK. The other difference in work cultures that I noticed was the working hours. So in the UK, we generally work 9 to 5, unless there's a deadline coming. And if there's a meeting and it's approaching 5, the meeting is going to stop at 5. In Japan, the meeting doesn't stop at 5. It keeps going till we've discussed everything. And if that goes over a meal time, the meeting will just move to a restaurant. And I'm really happy that my supervisor told me this before I went, because I'm someone that gets really grumpy if they're hungry. So I could prepare accordingly for these evening meetings and help make them as productive as possible. The final one is an obvious one, time difference. Harry is 5 hours behind me, which I really enjoyed, because it meant I had time in the morning to do all my homework before we met. Japan is 8 hours ahead, which isn't very helpful at all for arranging virtual meetings, because the overlapping in working hours is very small. Some logistical tips that I use to tackle this: I put my collaborators' time zones on the calendar, so I could always see what time a meeting would be for them. And another thing I did was, for my Japanese collaborator, I always kept his favorite time just free, because he was the hardest person to meet with, so I gave him priority. And of course, we made the effort to visit in person. So over my collaborations, two main things became clear to me. And I'm going to focus on the sort of Japanese motivation for this, but the same is true for my collaboration with Harry. The first one is how taking the time to learn about and respect the other culture really pays off. So I started to learn Japanese on Duolingo. I didn't get very far at all. I didn't really get past the alphabet, really. But it really helped my understanding of the Japanese culture. And the second one is the importance of an in-person visit. It's the classic thing I'd read about, been told about, all these differences, but I couldn't really get a hold of them until I'd experienced them firsthand. I gained so much from my visit to Japan. Not only was it some collaboration time without time difference, but I think being surrounded by the culture and getting to experience it firsthand really helped my understanding of my collaborator and helped our collaboration going forward. Because I understood their life better and I knew what their perspective was. So of course, this is just based off my experiences, and there could be other differences, but the key thing to remember is to approach them with respect, and they will just be differences and not challenges. So that's in depth a potential challenge that I've experienced, but there are lots of other ones. For example, if there's lots of people involved in a project, it's simply logistically harder. So if you're in a meeting with 5 people and you want to hear from everyone, that meeting's simply going to take longer. Equally, it's a lot harder to arrange a meeting for 5 people than it is for 2 people. And that's backed up by a quote from my supervisor. He says, there could be a significant overhead as the result of a collaboration, especially when more than 2 parties are involved. Another challenge could be difference in experience. This could make communication slow, or it could lead to a misunderstanding. So that's something to be aware of. Another thing is lack of confidence. So as a PhD student, it might be hard to say what you think especially if you're disagreeing with someone more senior or someone more confident than you. Remember, just because it's said with confidence doesn't mean it's right. Overall, don't be afraid to express what you think. There's nothing wrong with being wrong, and aim to create a collaboration environment where you feel comfortable expressing yourself, no matter if you're going to be wrong, if you're going to be disagreeing with something. You feel comfortable being heard. Also, being too possessive or territorial can also lead to conflict. Remember, it's all about making the paper or the work in general better. It's not about who did what. All changes are for the good of the paper. So you should always feel free to iterate on the work of others with a view of making the work better. Finally, we need to take a moment to address the fact that sometimes collaborations can go really wrong. Collaborators in a position of power, perhaps because they're more senior or because they provide hard-to-find expertise, may abuse that power. Dealing with the power dynamics inherent to research relationships is really a topic for a whole other talk, which we're not qualified to present, but there's one piece of advice that we want to give, and that's don't collaborate alone. So we recommend always going into research collaborations with someone else you trust, for example, your advisor. Bad actors may see collaborations as opportunities to get free labor, elicit unwanted social relations, or build themselves up at the expense of others. Our community has programs like SIGPAP Plan Cares to help with problematic scenarios like this, but the immediate situation will be much easier to deal with if there's already someone you trust involved. So don't collaborate alone. The main thing to remember is to be kind. There might be other things at play. We've got another great quote from Nadia that I think really sums this up. I've had situations when in the heat of the deadline I swore I'd never work with this person again. But when the dust settled, I realized that what we've done is some of my best work, and I couldn't have done it myself and came to appreciate my collaborator very much. And this also leads nicely on to when collaborations don't work out, because the quote continues as, but there are other times when you realize that your opinion is simply not valued, and the final result is not worth suffering. Then you just don't work with that person again. If a collaboration doesn't work out, that's completely fine, and that's backed up by what my supervisor says. He points out that not all people can work well together, so expect some collaborations to fail. So don't worry if it doesn't work out, but Harry will now tell you the best way to create a successful environment for your collaborations.
Okay, so how do you make your collaborations as successful as possible? I think I wanted to address this by splitting this in kind of two parts. I think when you go into a collaboration, and especially if you're the one initiating it, often there's really a dual role for you in that collaboration. You're both a leader and a participant. And so I'm going to break it down like that and talk to you about how to lead a collaboration and how to participate in one. As a leader in a collaboration, I think people sometimes think of leadership as a power thing, but it's really not. Being a leader is having a responsibility to the group that you're leading to keep it organized and to keep it moving correctly. And so you should think of it that way. Anything as a leader that is blocking the team's progress is your responsibility to address. It's not necessarily your responsibility to solve that problem yourself, but it's your responsibility to make sure it gets solved. This includes issues with social dynamics, missing expertise, not enough person power to do the job. All of these things are things that when you collaborate, you should think about trying to be able to address. There's some logistical notes that might help with this. For example, scheduling regular meetings is a good way to keep everyone on the same page, and being on the same page with technical details that don't matter much, except you have to pick something. So for example, how a paper gets written or how versions are controlled and that sort of thing. Being on the same page and having it not be up in the air and undefined is really helpful. Another thing you need to do as a leader in a collaboration is set goals. So there are tangible goals that you could set, for example, being able to write a research paper or complete some code artifact. And then there are intangible goals such as, you know, everyone's learning objectives and also having fun. I think that's a good goal as well. For some of these goals, you're going to want to be pretty careful in the way you specify them. So there's this framework called SMART goals, which you might have heard of. A SMART goal is specific, measurable, achievable, relevant, and time-bounded. So to give you an example, suppose we're going to write a paper. Well, we need to be specific about what the topic of that paper is. We should be able to measure our success by the contributions that we are able to make. That goal should be achievable. So maybe we've already accomplished one of the contributions, which makes us feel like, oh, we can definitely move on and do the rest. We want the goal to be relevant. Maybe we want to submit this goal to POPL, submit this paper to POPL, which is relevant to our career goals and things like that. And then time-bounded. The POPL deadline's in July. Let's make sure that's done by July. Of course, this is research, and things are fuzzy, so you may also prefer to make the goal smart-ish. Maybe the topic isn't perfectly defined, or one of the contributions is, as of right now, missing. Maybe you don't exactly know where you're submitting this paper or when the deadline is. But the point is to think about these things and go into a collaboration intentionally, sort of with a clear idea of what you want to get done, so that you sort of know when you're done and you also can succeed at it. Another thing that's really important as a leader, and I touched on this a little bit before, is that delegating tasks is super important. Every task needs a point person, someone who's willing to do the heavy lifting on it. And often, if you don't know who's in charge of the task, it's probably you. That doesn't mean you have to do it, like I said, but it does mean you have to figure out who is going to do it, which means you need to delegate. And this can be kind of hard and awkward as a PhD student. Sometimes you need to delegate tasks to your superiors, to your people who are your senior. But actually, I think it's really valuable to learn to push through that awkwardness. First of all, I think the senior people in your group will appreciate that someone has a top-down view of the project and that they're sort of told what is needed of them. But also, I think that this has been a real competitive advantage for me in my career, is sort of taking the initiative in those situations and just saying, okay, here's what has to get done, and just telling folks what needs to get done, so that everything actually does get done. Then as a participant in a collaboration, it's really important that you know what your strengths are. So this is a quote from Benjamin Pierce. Different people have different strengths. If you find out what you in particular can bring to collaborations that's special, then that's great. For Benjamin, it's the skill of being able to imagine himself in the position of someone that doesn't already understand what they're trying to explain, because it helps to make sure that everything's explainable to everyone. For me, I tend to be good at sort of painting the high-level picture of a project and dealing with the organization and that sort of thing. And when you're in a group, you want to try to make sure that those strengths work well together. So for Sam's and my collaboration, we are both pretty organized type A people with a good top-down view. And so we sort of understand how each other think, and it was really easy for us to collaborate because of that. On the other hand, when Sam and I write talks together, our strengths complement each other. Sam is much more creative and excitable, whereas I'm quite a bit more serious, and I try to rein some of that in.
The fireworks were too much. I see that now.
But either way, whether you're playing off each other, sort of synergizing your strengths, or playing off each other's strengths and working together in that way, the point is to just know what you're good at and what your collaborators are good at, so you're working with those strengths instead of against them. To measure success, did you achieve your SMART goal? Was the experience more enjoyable than it was stressful? That's a hard one. And do we want to continue collaborating? Or at least would we be open to in the future if there was an idea to collaborate Ohad says that in a successful collaboration, everyone feels like others have done more. And I think that's really true, because if you're collaborating effectively and multiplying each other's potential, then no one feels like they've done that much, but the project gets done and everyone's happy with it. The whole point is we couldn't have done this alone, so I want to thank everyone who contributed quotes and ideas. We really appreciated it.
So now go back to your research groups and discuss how you can get started with collaboration.
Thank you.
We have time for questions.
Thank you for the wonderful talk. I especially appreciated the section on recognizing challenges, and I was wondering if you had any insights on how to resolve conflicts if you already find yourself in the midst of one of those challenges.
Yeah, it's a great question. I think at the early stages of conflict, openly communicating is really the best option, sort of making it clear that there is something that isn't going great for everyone, and being sort of non-judgmental about it, and not sort of jumping straight to this is the worst person ever, but instead sort of dealing with this with communication. If things have sort of devolved past that point, I think this is a great instance where the don't collaborate alone idea is important. Having an advisor in the loop, having folks who can help to mediate conflict is also really valuable. I mean, I don't think there's anything unique about conflict resolution in research settings versus conflict resolution in general. It's a hard problem, but that's my general take.
It's all about just expressing how you feel and how, because you're in charge of how you feel, but don't be like, you made me sad. Just say, I don't feel comfortable with this, and just explain your position in a sort of like a non-confrontational way. And if you don't already have someone you trust involved, hopefully you have an advisor that you can go to and go, this is a scenario, can you help me navigate this? And hopefully that would help.
Thanks for the great insights.
Yeah, so maybe a bit of a tricky one, but I guess, do you have any advice on, like, if you're managing your own collaborations, how to deal with things like authorship order, and that kind of thing?
It's another good thing to just discuss up front. I think the earlier things are brought up, the easier they are. Like if you get all the way down and then something comes like out of the blue, it's never as good. Whereas if things are like if everyone is always on the same page, that's a nice, easy way to deal with it. It's like the classic rom-com where someone tells a lie and it grows and grows and grows. As long as you're always honest and open, hopefully you won't get into that scenario.
Yes. Oh, as in like sort of methods for deciding sort of in the first place if there's a collaboration starting, like, oh, in terms of, I guess this comes along with like expectations for what sort of role people are taking, or like initially if it's like everyone's on the same page, do you just say, oh, everyone is like co-first author unless things change, that kind of thing?
Yeah, I think so. First of all, different sub areas have different kind of expectations for this kind of thing. But the approach I usually take is like, you know, professors at the end and students at the beginning, and then sort of order it based on contribution, or alphabetical if there's nothing else. We actually had this come up in the paper that we wrote together, is we had sort of written an initial version of it where Sam and I were co-first authors, and then sort of the last draft of the paper I felt I had done a little bit more work on, and so I asked Sam, is it okay if I'm first author on this one? And we just worked that out and just communicated about it. But I think there's, you know, it's not cut and dry. It can be weird, but I think if people, if you try to keep people's egos out of it to the extent that you can, it all goes a little bit smoother.
And another thing to be aware of is the cultural difference between different countries. There's different sort of what normally happens. If you make sure you're aware of what normally happens, you won't hit the point where it's worse when people are surprised. When Harry came to me, I was like, yeah, fair enough. And it's fine when people aren't surprised, but I think surprise can normally make people less comfortable.
Thanks for the great talk. One thing that I really liked that you guys talked about was your research strengths and playing to each other's research strengths. One thing that I'm curious about is how you discover what your research strengths are. For people who aren't as sort of introspective and self-knowing as the two of you might be, how do you sort of figure out among the many tasks in research, which things you think you can contribute to best?
That's a really great question. So, one thing is, like you say, for people who aren't as introspective as, well, I think I'm not by default. Actually, in undergrad, I took a course on leadership, and in part of that, we spent a bunch of time introspecting on our own strengths as leaders. So that's sort of how I know that. As far as my strength as a researcher, I think those often come from, by working on something over and over, and you start to see what you're good at. But I think that like all of these are just processes of taking a lot of time and being very intentional and just paying attention to, when do I feel like I'm really in my zone, in a leadership situation or in research is just when you're like, wow, this really feels good. Take a note of that and think about why that is.
Hi. I have a question about authorship that's really related to authorship, but more specifically on the dissertation. You are two PhD students that collaborate, right?
Yep.
Would you really recommend to two PhD students to collaborate in the sense that in the end what goes in the thesis must be unique and you can't really share, generally you can't really share what you contributed to. So would you really recommend logistically for two PhD students?
I think it depends on your country or your university's requirements for your thesis. So my university actually would allow me to put some of that work in. I have to say it was a collaboration, it wasn't just me. So I have to put that caveat in, but it is ultimately research that I contributed to during my studies, and for my school, that counts towards it. But also, I would recommend it because I had a great time and I learned a lot. And then if I'm gonna go do a solo project that I need for my dissertation, say, I've learned so much from this experience that it really helped me.
Yeah, I'd say another way to make it a little bit easier logistically is if a more senior student is collaborating with a slightly more junior student. I've had this experience a couple of times in my PhD where I'm sort of leading a project that a newer student comes into, and it's clear that that'll go into my dissertation because I'm the one who started that work. But then later on, the other student is doing their own work, and maybe that's not what I'm doing anymore, but I keep collaborating in the background because I like working with that person. And so like I think that if you're worried about those sort of logistics, getting yourself sort of into collaborations where you'll be able to trade off that first authorship role is also helpful.
I think maybe we should cut it off there. Thank you very much, everybody. We have a 30-minute break now. We will reconvene at 4 p.m.
Welcome back to PLMW. I'm excited to introduce Neil from the University of Cambridge, who is going to talk to us about giving a good talk. Very meta topic.
Yeah.
Here.
Should it show up on here? Ah, there it is.
We're good.
Okay, perfect. Okay, hi everybody. I'm a lecturer at the University of Cambridge, and I guess I've been working in PL for about 20 years now, which is a little hard to believe. And so what I'm going to talk to you today is about how to give a scientific talk, and to do that, I'm going to first start with, why we even bother. So the reason that we have to give talks, it fundamentally comes down to the fact that that science is a collective endeavor. So, no single human brain is large enough to understand the universe, and so we all have to go to it, work at it together. And if you want to work together, you have to talk to other people. And so, it's not the only mode of scientific communication, but it is one of them. And pretty much anyone who works in science is going to have to give some talks sometimes. And so, if you have to do it, you might as well get good at it. And so some of the, so you can think about scientific communication as like, sort of living on a spectrum. At one end, you might have individual conversations, maybe with your supervisor or a trusted teacher or mentor. And these kinds of communications are really good because, it's a dialogue and you're talking to someone and they explain something to you. And if you're confused, you can ask questions, and the person you're talking with, or you for that matter, can adjust your approach based on how the other person is responding. So that's great. And when you can do it, you should do it. But, we're computer scientists, we worry about scaling, and talking one-on-one just does not scale very well because you're talking with one other person. Sort of at the other extreme is the scientific literature. So, you have a published paper, and there's no dialogue when you're reading a paper, but it does have another key advantage, which is that, like, once you've written something down, you can go back and look at things. So if, on page 15, there's some surprising claim about an equation, you can flip back and look at the equation on page 3 and figure out, like, just whether they were right or wrong. And the other thing is, papers actually scale really well. So even after I'm dead, you'll still be able to read my papers. Lectures and conference presentations and things like this, they're somewhere in the middle. And in some sense, they combine the weaknesses of both approaches. So, like, I'm talking to a room of people, and the number of questions is relatively few, and you can't refer back to things that I've said because once the sound waves have died down, it's gone. It has to live in your memory or not at all. But they still have like a really important value because they are a lot more personal than papers. So just as an example, actually I'll give 2 examples. So at the last ICFP, I was sitting next to Stephanie Wyrick, and I had mentioned to her a couple of days before that there was something about graded type theory that I didn't understand. And so while the speaker was talking, at one point she just poked me in the shoulder and said, "Hey, look at that." And she pointed at one particular rule. And then when I looked at it, all my confusions were clarified. And if you have a published paper, the paper has to explain everything. And so it's very difficult to draw your attention to things in the way that a speaker can. And secondly, we're actually just, human beings, and we have like sort of an emotional nature. So my favorite speaker of all is Gordon Plotkin. And objectively, he's a terrible speaker. Like, his material is very technical. His slides are stuffed full of equations, and he always overruns. And he's still absolutely my favorite speaker because he's so happy every time he speaks. Like, the joy of the work that he's doing just shines through. And at the end of the talk, I leave feeling, yes, this is how, semantics is a worthy way of spending my life. And that kind of energy and emotion really matters because the stuff we do is hard, and you need that kind of motivation and energy in order to persist at it. And that can be communicated in a way that that's difficult to do in written communication. Okay, so I said before that, like, giving talks is very difficult because you can't refer back to things that you've said very easily. Speech goes away in a way that the written word does not. And secondly, it's difficult for a large room of people to ask questions. So feel free, I'm going to tell you all, feel free to ask a question whenever you want. And most of you will take this on board, but you will still feel naturally shy about asking questions. And I might get 6 or 8 or a dozen questions in this talk. And that's just way less than you'll get in an individual conversation. And so the consequences of these two facts are that it's often, you have to be very careful when you're giving a talk, because when you're describing something technical, even a small lapse of attention can cause a loss of comprehension. And if we know anything about human beings, it's that human attention lapses all the time. We're not like machines, we're people. And when I say human attention lapses all the time, people often have this idea that it's all because of phones and the internet and things like this. And that's not actually true, because human attention lapses for many, many reasons. Some of them are purely physical. The audience member might be tired or hungry or thirsty, or maybe they had a bad breakup and it's really messing with their head. Or maybe the talk is just too hard and it assumes all kinds of background information you don't have and you can't make heads or tails of it. Or the opposite problem happens also. Like if the talk is too easy and your audience feels like they understand everything already, they're like, okay, this listening here is a sort of a waste of my time and I'm not going to pay any attention. And so another thing that happens is, when you're talking about complicated technical material, it takes a significant investment of mental energy in order to be able to follow the talk. And if you don't really communicate a solid motivation to persuade your audience to invest that energy, then they're not going to. So if your motive is unclear, then you can't really explain difficult material to people. So the point is that when someone pulls out a laptop or looks at their phone, this is a symptom rather than a cause. And so that means that we need to focus on managing attention as sort of the key difficulty of a scientific talk. And so how do we manage human attention? So, people have been doing it for literally tens of thousands of years, probably long before, even fabric was invented or something, maybe hundreds of thousands of years. And the way they do this, or the way that people hold each other's attention during conversations, is by telling a story. So your story has some sort of question which raises some sort of situation which raises a question in the reader's mind. So if I'm telling my daughter a bedtime story, what she asks is, what happens next? And then when I answer the question, so I say, oh yes, the little girl escaped from the bear by falling into a big hole, she has another question, which is, okay, now what happens to the girl? Does she get out of the hole? And so by asking questions whose answers raise further questions, you can hold your audience's attention. So you can use narrative to sort of help people follow your talk. And what I mean is, you don't need to be Vladimir Nabokov or Jane Austen or somebody. Even though Nabokov did publish scientific papers, he loved butterflies and he published in entomology journals. But it wasn't florid, beautiful prose in his scientific papers. He was describing a butterfly. And the reason is that the way that the narrative structure that you give in a scientific talk, it doesn't need to be very complicated. So you only need a very simple narrative structure. So I'll give an example for the sort of talks we'll see in POPL. I did 20 minutes here, but I think, is it 15 minutes this POPL? I can't remember. So it's 15, 20 minutes. This is a typical conference talk. And so the way that you want to structure it is you want to open by giving some motivation for what you're doing. So you've done some complicated thing and you want to tell the world about it so that other people understand it and sort of the understanding waterline of humanity is raised. So you want to explain what are the problems that you're trying to solve and why is it important to solve this problem. And so that will hopefully get your audience to think, yes, this is an important problem, it's worth solving, now I want to know how. And then what you want to do is you want to give sort of a kind of a roadmap to solving the problem. So this is going to be not a specific detail right away, but just a high-level overview. And so you want to explain what you did in general and what ideas underlie this approach. And you want to have a high-level roadmap because when you get into the technical material, you need to justify to your audience, yes, I see that there's a plausible approach. It's worth devoting the attention to it, and that's in the rest of the talk. But also, anytime you do a piece of scientific research, you're describing what took you a year or 2 years of work to do, and you had lots of ideas during that time. And in your talk, you only have time to explain one, maybe two things. And you want to get that penumbra of stuff in your audience's mind so that they can say, yes, the thing that you're doing makes sense, and there's also more stuff for them to learn in the rest of the paper. And so then after actually explaining your, one of the technical ideas in your paper, you can close with a conclusion where you contextualize what you've done and relate it back to the problem. So you can see how the thing that was done connects back to the original motivation. And then you can let your audience ask questions if they haven't been already. Okay, so let me focus on motivation. This is actually going to be the biggest part of my talk because it's actually one of the most important parts of the talk because even sitting through a talk is an investment in your audience's attention, and part of what you're trying to do is you're trying to communicate to them that this little bit of attention is for them to judge whether they should devote much more attention by actually giving your paper a close read. And so in order to figure that out, you have to explain to them the problem, the motivation. And so fundamentally, it comes down to answering two questions. So what is the problem? And second, why should anyone care? It's easy to make up questions. It's more difficult to come up with the reason why you should care about the solution. But you have to answer both of these questions in the audience's mind before they'll be convinced that it's worth the effort of paying attention to the speaker. And so what I mean here is really your audience is giving you a gift. They're giving you the gift of attention, and you need to demonstrate to them that their trust in you is not misplaced. And so there's sort of two main styles of motivation in scientific talks. And you can think of this as the top-down or engineering view, where you say, here's a problem that obviously needs to be solved. How do we solve it? And then there's also a contrasting style, which is the bottom-up, or what you might call scientific style, where you say, here are some puzzling observations, and there's some sort of tantalizing connection between them. How can we understand this relationship better? And so what I'm going to do is I'm going to go through two different talks and sort of give you an example of how this kind of motivation can work. So for the top-down motivation, the key things you need to do is you need to really lay out the problem and make clear why this problem has to be solved. And so once the audience has bought into the question, bought into your question and want to know the answer, then they'll be ready to join you on the search for the solution. And so, there's also when you try this style of motivation, there's sort of two dangers. You might fail to articulate the problem, or you might even just take too long to get to the problem. And so let me give you an example. So this is a paper that my co-author, Jana Dunfield, presented with me in POPL 2019. And so it has a very long title, but it's fundamentally about type inference. So I'm going to tell you a little bit about it so that so that you can understand like the shape of one of these motivation sections. I'm not claiming that this is a perfect talk, but like I want to show you a real talk, not necessarily the ideal. And so what I did was I said, okay, I'm going to talk about a fancy type system feature called generalized algebraic data types. And what are these data types? Well, they're like a normal data type in a functional language, except that you can add additional information to your type. So here we have vector. This is sort of like the hello world of generalized algebraic data types. We have vectors, which are length indexed lists. And so if you look at the type of nil, what you see is that this is a, a vector of length 0 right here. And so that's the type of nil. And the type of cons says that if you give me a head element and a vector of length n, the result is a vector of length n plus 1. And so that looks very obvious, but it lets you write some really cool programs. So for instance, here is a very small but cool program, and this is the head function. So if you're given a non-empty list, it'll give you an element. And it'll do so by giving you the first element in that list. And so you're thinking, okay, that's fine. But the thing that makes this really cool is that this is a whole program that will never crash. It's a complete set of pattern matches. You don't need to match on the nil case because it's impossible. And so this, and then you can, then like, the normal functional programs on lists are going to do things like their types will give you additional information. So like map is going to preserve the length of the list. So if you give it a list of length n, mapping a function over it will produce another list of length n. And other functions like filter, you can say, well, okay, when you filter something, you give it a predicate in a list of length n, and because the filter function can drop some elements, you're going to get out a possibly smaller list. And so you can see that this is a really cool feature to program with, and now that I've explained what the feature is, I can explain what the problem is. And the problem here is that like implementing fancy type systems is very, very hard. And you need a lot of specialized expertise to do it. And if you have that expertise, you are probably on a first name basis with one of 3 people. And the point here is like, now here is the problem. As scientists, we want information to be like universally available, and we have like this really cool thing which is sort of transmitted master apprentice style. So that's a problem, and it needs to be solved. And so you can see that the motivation here is top down. So here is a problem, we really need to solve it. And so now I'll give you an example of a bottom-up motivation where we start with some fascinating observations, and then we observe some surprising connection, and now we're motivated to understand why this connection exists. And so the dangers here are like sort of conversely, are sort of the opposite of the ones for the top-down exposition. And so the first danger is that like, a collection of random facts is just going to be boring. Like, why am I getting hit with random facts for a long time? And the second the second problem is a little bit more subtle. And so the second problem is like sometimes for like, super experts, the connection is immediately obvious. But if you're less expert, the connection might be opaque. And you're like, okay, well, these people are super excited, but I don't understand why. Okay, so now I'm going to give you my absolute favorite example of one of these kinds of bottom-up motivations. This was a talk given about 10 years ago by Noam Zeilberger, who's a researcher in Paris. And what he did was he said, I'm going to show you a connection between the lambda calculus and maps. And so what does that mean? And so what he did was he said, okay, what I'm going to do is I'm going to look at a certain class of the lambda calculus. I'm going to count the number of lambda calculus terms that have one free variable and are linear. And so if you have one free variable, if you're allowed to have one variable, one of which is free, there's exactly one such term. And if you move up to 2 variables, one of which is free, there are 2 such terms. And if you go up to 3 variables, there are 9 such terms. And here he's enumerating each of these variables. And then he says, and if I if I go to 4 free variables, then I get 54 such terms. And so you can see here that this is, at first, a really eccentric thing to do. He's picked some strange lambda calculus, and now he's not even running these programs. He's just counting them. And so, this is a peculiar thing to do. And then he says, OK, well, I have been counting these terms, and I have a sequence of integers. Here's what I'm going to do. I am going to stick it into the online encyclopedia of integer sequences. And we're going to see what it tells us. And what is the sequence that starts with 1, 2, 9, 54, and then he wrote a computer program to count these terms, 378, 2916. What is this sequence? And the OEIS says, this is the number of router planar maps with n edges, or n vertices. And so what are those? Well, let's draw some pictures. So a rooted planar map was a thing invented by Bill Tutte, who's like one of the most famous graph theorists of all time. And he invented it in the 1960s, and what it is it's a graph that you can draw on the plane without any edges crossing, and where one of the edges is distinguished. That's the one with the arrow. So you have a planar map here. And then if you pick out one of the edges as special, then it's a rooted planar map. And he wrote a paper on how you can count these things, which is where this series on the p-reviews page came from. And so then he said, OK, let's take a look at these things. And so here's the rooted planar map with one vertex, then and then 2, and then when you go up to 3, you get 9, and then when you go up to 4, you get 54, and now we have established that there's this shocking connection. So you have the lambda calculus, or the linear lambda calculus, which is a thing people know about and use for various purposes. Like if you've programmed in Rust, you've programmed in a basically linearly typed language. And now here is Bill Tutte, decades before the linear lambda calculus has been invented, and he's come up with something that's isomorphic to the linear lambda calculus. And at first glance, there's no connection between graph theory and lambda calculus, and yet here it is. And so now what Noam has done is he has established a relationship between two disparate things. And now, if you have a mathematical soul at all, you're thinking, what the heck is going on? I have to know what's happening here. So in other words, the point of a motivation of the motivation of your talk is to identify a problem and convince your audience that something interesting is about to happen, or the answer to this question is going to be interesting. Okay, so now you've motivated your talk, and you've convinced your audience that there is a problem that they have to know the answer to, or they'll be irritated with you. And you have to explain what you did. And what you want to do is you want to give an overview of what you did, so that the audience understands the landscape of your solution, and then you want to identify one particular key idea that you're going to go into more detail with. And so if your motivations section has been successful, they'll be intrigued with your problem, and they want to know the answer. And so at this point, you have to start telling them what the solution is. But the thing is, you can't tell them everything. Like I said, a paper typically describes a year to 2 years of work, and that can't really be summarized completely in a 20-minute talk. So you need to tell them something, and should tell them one thing. And the reason why it's 1 is because it can't be 0, because you have successfully convinced people that the solution to this problem is interesting. And if you fail to tell them anything, they're going to be mad at you. They're like, OK, you've convinced me that I want to know how to do type inference, and now you've told me nothing about how to solve the problem. I'm mad at you. The other mistake that people make is that a typical advance is going to require several innovations, and if you try to explain all of them, your audience will get confused. because we're human beings. We learn things a bit at a time, and if you get hit with a wall of ideas, then you can't integrate one idea before the next one comes, and you end up assimilating nothing at all. And so so if you try to explain too much, your audience will be confused, and they won't be able to take anything away from your talk. Just like if you didn't tell them anything. So tell them something, but not too much. And so here is an example contribution slide. This is from my 2019 talk. And I said, okay, and so you can see up there at the top, I set out the question, can we find a type system for GADTs that fits in one paper and that you can read and then implement? And I said, oh yes, of course. What you need to do is you need to use the Curry-Howard correspondence and then add a sprinkling of structural proof theory, and you'll be able to get the type inference algorithm that you want. And then a little bit later, I laid out all the different pieces that went into the solution, and I highlighted a couple that were going to be in the talk. And what I want to do here is to say, actually, this contribution slide isn't perfect. I combined the big question with the technical approach, and when it would have been better to separate them, to give the audience some time to assimilate what's going on. And there are no examples right there either, because people learn generalizations from concrete examples. But it does the job. Humans are finite. Conference sessions are also finite, and because of this finiteness, there's always a tension between can I explain this thing better? And if I do, then the next thing is explained less well. So you have to pick your battles a little bit. And you shouldn't feel worried if you're thinking, oh, this isn't perfect, my audience will hate me. Actually, pretty much everyone in the audience wants you to succeed. They want to sit and hear something interesting, and they also understand that telling people how to do things is sort of an inherently stressful thing. So you should presume the goodwill of your audience, but you shouldn't beat it up a little bit. Okay, so now let's talk about how you should explain your key idea. And what you want to do is you want to explain something sort of interestingly technical in enough detail that the audience can get something from it. So ideally, you want them to understand something well enough that when they go and read your paper, they're like, aha, this makes total sense. And all those things I was confused about in the talk, they're explained right here. And I have the high-level structure in my head from the talk, and so this makes the paper itself much easier to read. But once you start explaining something really technical, you're in danger. And the danger is that lapses of attention damage comprehension, and human attention lapses all the time. Okay, so let's pause for a moment to look at a cat. This is not my cat. This is my brother's cat. And it paused to relax. Its attention has lapsed. And now after relaxing a little bit, let's come back and think about how we can explain our technical idea. And so because we are computer programmers, what we can do is we can say, we have a big problem. Let's break it up into smaller problems and solve them individually. We can appeal to recursion. And so what you want to do is you want to divide your big idea, the thing you want to explain in detail, into smaller pieces, and you treat each segment of your exposition as a tiny little talk in its own right. And what you want to do is you want to start with a motivation, explain the idea sort of contextually, actually explain it, and then close with the conclusion. And so the thing that's going to save your audience from losing attention is that your motivation and conclusion, for each segment, are going to link together. So you're repeating what you've said so that anyone who's zoned out for a second can be brought back up to speed. And for the people who didn't zone out, it's actually helpful for them to understand why the thing they just understood is actually a useful thing to do. And so you're reminding your audience of what you did and why, so that they can stay with you as you speak. All right, so now what you want to do, so I'll give you a tiny little talk segment. So this wasn't supposed to be a technical talk, but you're going to get some anyway. And so what I explained in one piece of the type inference algorithm I explained was something about existential types. And if you don't know what they are, like, I'm about to explain it to you. So what I did was I said, okay, we have in logic universal and existential quantification, and when you're defining these fancy GADT data types, you turn out to need existential quantification in order to express these GADT constraints properly. And so, look, there's an existential type, and it lets you do things like information hiding. So a list of unknown length is the same as saying, oh, there exists an n such that I have a vector of length n. And these existential types are actually really important for programming with GADTs. So for instance, in the filter function, what we're going to do is we say, okay, for a list of any length n, the result of filtering is going to be a list of some length k. And so now we have a type that has both for all and exists in it. And historically, people, when they've seen type systems with both of these features, they've run away because it's really hard. And so now I have set up the problem here. I briefly explained what the issue was, and I explained, like, what the problem is here. And so here, I want to point out here. So I want to say, since I've gone into the technical section of the talk here, like, the reminder of what existential types here was like relatively brief. So, a type theorist will say, ah, yes, I understand this. But if you're not a type theorist, you'll probably be scratching your head. And in the technical part of your talk, it's a little bit okay to do that. Like, ideally you want everyone to understand everything, but as I said, it's always a compromise. Okay. And so now we have established what the problem is. This is hard. And now we're going to explain that it's actually harder than you thought. Because when you have a fancy type system with quantifiers, we also want type inference. So if we have a toString function and a map function and a vector, we want to write map toString over x's. We don't want to write something where each of those quantifiers gets explicitly instantiated by the programmer, because then half the program has turned from actual code that does things into type annotations. And so now we need to model type inference using this feature called subtyping, where we say, okay, we have this polymorphic function, but we want to use it as a concrete type, and we'll model that with subtyping. Again, this is an idea that is relatively familiar to experts, and now they're being reminded of it. So we're in like sort of the weeds of the talk here. So the reminders of what the problem is can be just a little bit terse, because you have only so many minutes. And so what I did was I said, okay, well, look here, this is the normal thing in type inference. And then when you add existential types, it's the similar, except everything gets dualized. And then when you have a language with both of these things, you have both the for all rules and the exist rules. And this is the place where you're going to have some problems. Like, it's easy to stick both sets of rules in the system, but it creates a problem. And the problem is that, like, the order that you can use these rules in becomes ambiguous. So, you can, if you're checking that for all A is a subtype of B, then there's two possible ways of doing it, and neither one is strictly better than the other. So you can guess the for all first and then the exists, or the other way around. And now we have a problem, because when you have two choices, an algorithm may have to try both. And this has created backtracking in your algorithm, because if you have multiple places where these quantifiers can occur, you have multiple places where backtracking can happen. And this would make your algorithm exponential time. And nobody would be happy with you if you did that. And so now I've explained what the problem is and said, okay, now exponential time is bad. I've created the motivation for wanting a solution. And now I can say, okay, well, now here's my high-level exposition. Again, it's going to be fairly technical, because we're in the actually explain technical bits of your talk. And I say, oh yes, there's this thing called polarization or focusing, and it divides everything into positives and negatives. And now what we could or values and computations. And with this separation, what you can do is take the old ambiguous rules and you can make them unambiguous by separating it into two relations. And you only use one set of rules at a time, and they can never interfere with each other. And so we've eliminated the ambiguity, and we've solved the problem of making the subtyping relation syntax directed. So exponential time is gone now. So what you can see here is that like the explanation of this one feature was actually a micro talk. So the key idea was divided into a couple of pieces, and I treated each piece as like a tiny talk in its own right. And there was a beginning, a middle, a motivation, some overview, and then like a solution, and then like there was a bit of contextualization at the end to say, why has this actually helped? Okay, so now you have fully explained a deep technical idea to your audience, and now everyone in the audience is a lot smarter than before. So you're done, right? Well, no, because you can think of what's happened in the talk so far as like you've climbed up to the top of the diving board and you've jumped into the ocean, and now as you go into more and more technical depth, you've gone deeper and deeper into the water. And now you need to come up for air again. And so the goal in your conclusion is you want to contextualize the technical stuff that you've did so that the audience understands what's happened, and then you want to remind them that there's more stuff in the paper, more things that you need to understand in order to actually solve the problem, and you want to set the audience up so that they can successfully ask you questions once the talk is done. Okay, so what does contextualization mean? So what this means is that you've explained something hard, and what you want to do is you want to explain, okay, why did I do this, and how does this solve the big picture problem that I set up at the beginning of the talk? So let me show you how I did this. So what I did in my talk was I gave one slide where I said, okay, you've been hit with a wall of type theory, and many of your heads are hurting. So was this too much? And I said, okay, well, the goal of our work was to build a type system that you could read one paper and implement. And here's somebody who I've never met, who just emailed me and said, hey, I read your draft and I implemented it. And he was an undergraduate in India. And so now this answers the question that I set up at the beginning, which is it possible to turn this feature into something that doesn't require like transmission via a master-apprentice chain? And so now the reason why we went into this technical detail is justified in terms of like the higher level outcomes. And as I said before, like, any paper is always going to have more stuff than fits in a talk. But if you've successfully explained something interesting to the audience, they're excited. They're like, yes, I can see that this thing that you explained is definitely going to help solve the problem. But it's also sort of clear that it's not enough by itself. And so what you want to do is you want to tell the audience what's in the rest of the paper so that they'll understand whether it's worth their time to invest in that. And the other thing you want to do is you want to actually summarize your talk on the last slide. And this is because people can't flip back to the previous part of your talk. So if they have a question, as they're watching the talk, some questions might arise in their mind, and then as time passes, like the question is washed away by like your sparkling words. And so if you put a summary slide at the end, then that'll remind them what was in the talk, so that they can ask their questions to you. So in other words, never ever end on a slide like this or like this. What you want to do is you want to break the rules of presentations and hit them with lots of text, because the text is there to help the audience remember what you said so that they can remember what confused them and they can ask you questions about it. Okay, and so now let's conclude this talk. And I'm going to hit you with that wall of text. So remember that a talk is about managing attention, and that you want to motivate the problem so that they want to know the answer, and then you want to give them the lay of the land, and then explain the technical idea by breaking it into tiny little talks that repeatedly motivate the thing that you're doing and connect it back to the larger questions. And then when you finish the talk, you want to put them in a place where they can ask you questions and remember what you did. And now I should be able let's see if I've got time to take any questions. Ha, perfect, I do have time to ask you. So, I'm happy to take questions now.
Let's all thank Neil.
So what is the connection between the graphs and the linear lambda calculus?
So what is the connection between the graphs and the linear lambda calculus? So it turns out that you can think of like the rooted edge as like being equivalent to the free variable, and Noam has a long series of papers going into more and more detail about this, and they're really cool. And it even turns out to have some neat applications, because people doing synthesis often want to enumerate programs in order to learn things. And hey, look, combinatorists have spent like maybe hundreds of years working out how to enumerate things. So it's really quite slick.
Thank you for the talk. It was really good. I was wondering, you gave when you gave the overview of all this at the beginning, you made a little. You gave the times, and I guess it's an approximation of the time it should take. Would you say that it generalized to talks that are longer or not? Like proportionally?
Yeah, so the thing to remember is that the times I gave are actually a rule of thumb. Sometimes, the reason why a problem is interesting is like is going to be really obvious to your audience. So like, if you solve P versus NP, then you don't really need to spend a lot of time explaining why this is important. But on the other hand, it is really worth spending a considerable fraction of your time, explaining the high-level problem and what your motivation is, because the number of people who understand the really deep technical parts is not going to be very high, because if you look at the POPL audience, there's going to be people doing like category theory and separation logic and proof assistance and static analysis and finite model theory, and anyone who's an expert in one of those will find the next thing over to be super hard. And so so the opening of your talk is your chance to teach people who aren't, like super experts in your area something interesting as well. So it is actually worth spending a good deal of time on that.
Okay, so you're saying for a 1 hour talk, it's also worth taking a good chunk of that during the introduction.
Yeah, that's right. Because longer talks are often things like seminar talks or keynotes, where you have a bigger audience of people who are often are not experts. If you're visiting a research group and your closest collaborator and his 4 students are there, then you can get straight into the technical stuff. But typically, people from all over the department or a whole conference are going to be there, and it's worth explaining stuff to them.
All right, let us thank Neil again. So I'm just call you up to give James instructions. Well, just I figure it'll just be easier, because I was just like, what do I tell them? So May is new faculty at Princeton, and before that was at Berkeley, and before that at Cornell, and even before that at Brown. And suffice to say, I've known May for a while, and fun fact, we actually met at PLMW 10 years ago. So I'm enjoying the fact that I get to introduce May today.
You know what, I'm going to do this a lot. So I just want to show you guys, through transparency's purposes, that what I'm about to do is go to this slide and delete it. cool. Let's make sure this clicker works. And does this clicker work? Yeah, it does. There's no back button. There it is. Hi. How are you all doing? Can everyone hear me? Hey. Allegedly, I'm using the podium microphone, but I have no idea if it's on. It is. Cool. So I'm May. Like Anna said, I'm a new professor at Princeton University. And I'm here today to talk about something that I've done a lot of, which is doing research with undergraduates, both as an undergraduate student and as a graduate student hoping to mentor undergraduate students. So how many folks in this room have done research as an undergraduate or with an undergraduate student? Okay, I'm actually going to invert that. How many folks haven't? Okay. This advice will apply to all of you. Now, for the folks that have, let me just paint a quick picture of my own time getting research and doing research as an undergraduate. I remember on my first project, I would start with a graduate student sending me like a paper or maybe a list of papers, setting up a weekly meeting, and then saying, see you in a week. And I had a pile of papers to read, and I might have had some intermediate goals or deadlines, but they were kind of soft. And the real deadlines were pretty far away. Maybe a term paper at the end of a semester, or even a publication that I was helping with that'll happen at the end of a year or whenever July 7th rolls around that particular year, picking an arbitrary day about nothing in particular. How many of you had an experience like that? How familiar is this story to you guys? Reasonably familiar. I remember as an undergraduate having the distinct impression that research was important, but not really knowing how to fit it into my semester, how to make sure that it got the same kind of priority as my homework did, how to make sure that when I got stuck, I could work through it, and I wasn't just waiting till the day before every weekly meeting to really make progress on my research. But there's something important that I didn't know then and that I think I know now. And it comes down to changing the way that I think about what the point of doing research as an undergraduate was. It's not just about helping a graduate student or helping a professor work on one particular problem. It's about teaching. It's about learning as an undergraduate what it is to do research. It's about learning as a graduate student what it is to mentor, what it is to explain your research even to someone. It's about teaching what research is through experience. And this metaphor, this idea that this is a teaching exercise, to me also pointed out an implication. That if research over the course of a semester with an undergraduate student might feel more like an exercise in teaching, then maybe we can also think of it in terms that we all have a lot more familiarity with, in terms of a class. So for the rest of this 40-ish minutes, we're going to go through sort of pushing this metaphor to the limits. And I'll show you some examples of how the idea, hello, of course you may. A student that is not currently enrolled in a PhD program. Any student that is not currently enrolled in a PhD program, in my parlance, is an undergraduate. I'm including master students, even though that's definitely false. Because what I mean to say is that there's a clear divide between the ways that students who are not pursuing a PhD get involved with research versus ways that students who are pursuing a PhD get involved with research. And we're going to talk today about the interface between those two, when someone who is doing a PhD starts working with someone who's not yet doing a PhD. Hopefully that's helpful. I don't actually know what the term for this is in English outside of America. I'd be curious to know later. All right, let's talk a little about classes as a metaphor. So when you're a student and you go to take a class, and we've all taken classes before, what's one of the first things that you interact with, or one of the first things that your professor desperately wishes you would interact with? Well, it's a syllabus. It's a couple of pages that outline what your lectures will be on, when your assignments are due, and what sort of final assessment you might have. And for the purposes of this talk, our final assessment is going to be a final project, since that's closer to the research idea. It's a document, it's a plan. that sets out a desired learning objective and learning outcome, divided into a smaller set of objectives that will cover and teach some skills or knowledge that you want the student to walk away from. And importantly, those objectives, that skills and knowledge, what the class is teaching, is not the final project was done. There's something about it, something about why we're offering this class that's distinct from because there was a project at the end of it. What would the equivalent be in research? Well, the syllabus is a planning document, right? So the equivalent would be whatever your plan is for a semester of research with an undergraduate. Now, viewing a research project as something that has such a plan has a lot of implications about the research projects we do. Implications on how we select them. Implications on how we choose to onboard our students and get them started with projects. And also even implications on how to keep our students motivated throughout the semester. And through all of this, by the way, I say the word plan a lot. I want to just quickly take a step back and say, no plan survives first contact with the students. When I say things like we should build up a plan, we should metaphorize it to a class structure, we should think about a document right at the beginning, I'm not saying that this is a contract and exactly 37% of your grade will be participation. I'm saying that having that level of insight into what you want to do with your semester, whether you're an undergraduate student, having that level of insight into what's expected of you and how to fit this into your classes is useful. And that this exercise is not about having the plan. This exercise is about learning how to do the planning. And ultimately, you'll need to be really flexible as the semester goes on. Okay, disclaimer over. Let's talk about implications on how to select your project when you keep in mind research is teaching, maybe we should have a syllabus. Perhaps the most important part of a successful research effort is selecting an initial project. So what should we look for when selecting a project? Either if we're an undergraduate student looking for our opportunities, or if we're a graduate student looking to recruit researchers. The first, that we can identify an actual semester-sized project out of our huge research project. Honestly, there are a lot of ways to do this, but I find that one of the best ways to do it is to ensure that you have mature research. The more mature your research is, the more likely it is that you can do things like actually predict sub-goals that are likely to be necessary for your research to be successful. You could also have mature frameworks. If you have, say, a semantic framework for building out type systems, a good example of an undergraduate project would be to use that to build something with it. In all these cases, though, you're not just starting out. The most important part is that your project is mature enough that you have a reasonable idea of what done might mean for your undergraduate students. Okay, beyond knowing what a project is, we should know how to measure success on that project. So there needs to be some clear metrics for that success. This sometimes comes in the form of obvious things like finish this proof. But frequently the success that you're looking for with your undergraduate isn't about work done per se, so much as lessons learned. Ooh, can we close that door? Thanks, y'all. This is something that you can do, not close the door, measure success. It's something, it's something that you can do together, collaboratively, that a mentor and mentee can sit down together and really work on and work through. What else do we need? We also need to figure out the tools that are required to achieve success in a particular project. We need to be able to establish what the prerequisites of the project are, which in almost all cases is going to include at least something that's not taught well in a class, or at least something that you're not sure is covered in a class. This exercise is especially important when you're looking to work with faculty. As someone who is a professor at Princeton, I can confidently say that I've never taken a class at Princeton. I don't really know what's in them. I know the ones that are in my discipline maybe, but if I see you've taken data structures, I might incorrectly assume that that means you know how to write a red-black tree in your sleep. And that's not necessarily true of every data structures class. The last thing If the project you're intending to get help with needs to last more than a week or two, it's important to not just say, this is your one project, go, see you in 2 months, but to establish intermediate goals, to break down the project into a series of deadlines that are more tractable and that fit better into the structure of a semester. If you're a student that's looking for a project, the thing you should ask yourself is, how would I break this project down into goals? Do I know what I should have done next week or tomorrow when I work on this project? And let me reiterate for the undergraduates in the room, this isn't necessarily something you're always going to get up front. It is okay, and in fact, really necessary to ask for a lot of this information. It's a really good way to sit down with your professor and mentor or your graduate student helper and start paving the pathway for success in the project for yourself. We are somewhat busy, somewhat scatterbrained people who don't necessarily realize that we never told you that you can't work on this until you've read Tolstoy's War and Peace for some reason. Okay, lot of advice, rapid fire. Let's take a step back and look at some examples that we can hopefully generalize by, because apparently that's good, according to Neil. So I'm going to have 3 examples, and this one particular example will have had 2 tries. So for a while, for a few years, I was working on building out a new type system. Technically speaking, it was a substructural type system that ensures destructive race freedom for concurrent shared memory programs. Much less technically speaking, much less technically speaking, it was a type system, kind of like the one that you have in Rust, which proves that multi-threaded code is always thread safe, even if you do some mutations. I wanted to take this larger research project and divide it into a couple of undergraduate-sized semester-long projects, say. Let's look at how I succeeded on doing this, focusing on those criteria of seeing if the research was mature enough to yield a project, whether we had an idea of how to measure success on the scale of the undergraduate work, whether we had a sense of what the prerequisites for the project were, and whether the project was divisible into deadlines. Okay, story number 1. The first time I tried working on this was at Cornell University. I was approached by a master's student who wanted to do a master's thesis, and I said, sure, that sounds fun. I'm working on this new type system for concurrency. You can help me with that. The student approached me, and I said yes at a pretty early stage of the research. In particular, I hadn't actually figured out, like, from a technical angle how this whole thing would work. I didn't necessarily even know it would be substructural yet. I could have thought of it as any kind of ownership system. What I had was a syntax and a bunch of examples of things that I wanted to make sure worked, and a bunch of examples of things that I wanted to make sure didn't work. As a corollary, I actually didn't really have a notion of what you would need to work on this. I didn't know what the fundamental technology was, and I didn't know how to onboard onto a vague nebulous cloud of the last 25 years of research in uniqueness and ownership. So the project I came up with was to tell the student to just go ahead and build an interpreter for this language. I thought, that'll let us test out my examples. That'll let us see sort of where the syntax that I'd also designed starts falling short, how annoying it is to use this even before we have a type system. Okay, that was the project. What do we think about our criteria? Well, it wasn't great. Because the research was so immature, while I could identify a project, it wasn't really clear how that project connected back to the research. Because it was so early that I didn't know how the type system would work, things like the syntax actually were probably going to change to adapt to the needs of the system, which would cause the overall semester project to drift further and further away from what the research goal wound up being. That in turn made it really hard to measure success on the project. While I guess in some sense you could say if you finish an interpreter, good job, it's not clear what that did to teach the student a lesson. The student had already taken compilers the class, and it's not clear what that did to further research. I also didn't really do a good job of onboarding. There's a book edited by, I think, James Noble and Tobias Rigstad on just like, here's how you do ownership and uniqueness papers. And that was the resource that I picked, and it was way too much for like your first week of reading. The only real saving grace here is that interpreters are great for deadlines. they're a driving structure of a lot of coursework in programming languages, so we tend to kind of know how to divide them into deadlines. Okay, that didn't work. But let's try again. So a year goes by, and I'm now at UC Berkeley, and I'm trying to recruit students again. At this point, I've spent months really working on the type system. It's way later in the project's maturity, and I've gotten to the point where the entire system is written out on paper. I'm pretty confident the rules work. I've even figured out how to divide the correctness questions about the system into a classical framework of progress and preservation and a dynamic semantics I've already written. What has to happen next is those proofs need to be done, which is itself a daunting task. But I had some good starts. I knew what invariants I would need to maintain and what inductive invariants those proofs would probably rely on. And I knew how to divide these proofs into subgoals and lemmas that honestly seemed like they would really work out. At this point, I could pretty confidently predict how much time it would take me to do this project and how likely it was that each individual theorem statement was actually true in my system. The project here, prove that progress and preservation, chase my lemmas around, see how it goes. How do we measure up now? Well, the project's much later, and because I've got all of these lemmas to chase around already, it's not that hard to see how I could measure success. Each of these lemmas will teach the student both something about how to prove this kind of property in a system, giving them experience in practical usage for programming languages papers, and further the research. It's also fairly clear how the system works. I know at this point what it is as a substructural type system. I know what it's like. I know what it's not like. I know what specific antecedents you need to learn. And in particular, I know which chapter of advanced types and programming languages you should read. Having already divided the proof means that each lemma can have its own deadline. So we had a good structure for running the entire semester. And all of this is really enabled by the fact that the research was more mature, that I had a good idea of where the pieces were and how they would all fit together before I tried to recruit an undergraduate. Okay, that's a good example. Question. Some of them are. The goal was not to mechanize them for the undergraduate work. The undergraduate about halfway through this project was like, hey, I've heard about this thing called coq. And I was like, I hope I know what you're talking about. And the students said that they wanted to try using that to mechanize the proofs. And I was like, you know what, let's do this thing. And the student got through a bunch of them and decided that was incredibly hard. And we didn't finish mechanizing it. Okay, one more example. This is from when I was an undergraduate student. So when I was an undergraduate student at Brown University, when dinosaurs walked the earth, I was looking for research, and I found that my professor, Sriram Krishnamurthy, and his graduate student, Joe Politz, were trying to recruit students for a new project, which was a tested semantics for Python 3. The idea behind the project is that we would take all of Python 3 and identify a core language that sort of captured the essence of that. We'd build a desugarer, a sort of translator that only works locally, from full Python to this core syntax, and we'd write up formal rules describing the operational semantics of the core language we'd designed. Ultimately, Python has its own test suite, which is very cool. So we could use the tests that Python used to validate its own implementations were real Python to check to make sure our implementation was also real Python. That was the project pitch. And the actual semester scale project for this one was, let's just do the whole thing. Which was a lot, but actually kind of worked out this time. Okay, why was this project a good idea? Well, it turns out that this wasn't the first time Joe and Sriram had done this. With just the PhD students, Joe and Sriram had previously built out a tested semantics for JavaScript, so they kind of knew what the flow of the project should be like. This was their second example of a successful strategy. For it to work, they knew they needed to have a robust and mature test suite along with a good infrastructure for writing the semantics themselves, something that was accessible to the students, which they had. They'd already developed that. The PLT group that Sriram is deeply involved in is very interested in educational tools. They also knew that this was such a big, big chunk that just kind of do all of it was a scary thing to tell the undergraduates, but they had this test suite, which they were able to divide down into different levels of semantic features and even different classes of syntax, which meant that we could use these tests to show the progress of our implementations, which would prevent us from feeling like we were just climbing up a hill that we could never see the top of. Between these tests and the fact that our research was based on interpreters, we actually had a pretty good setup for intermediate deadlines. This satisfies our criteria. While the project was entirely new, the frameworks we were working in were mature. It was basically just a second example of a strategy that had already worked. It was also easy to measure success. We literally had a test suite that could have a percentage of succeeding and failing. Additionally, it wasn't super hard to figure out what the prerequisites were because, well, the previous project. Whatever they needed to make the JavaScript thing work is probably what we would need to make the Python thing work. And like I just said, tests and interpreters are great for deadlines. So example 3, good research project. Let me take a step back, but not literally because the microphone's fixed. What do I want you to take away from these examples? Well, for current undergraduates, or really for anyone else who's looking to get involved with research, this is really about what to look for when you're selecting your projects, how to know what your project expects, and to know what's expected of you. And this is going to be a repeating theme. It's a call to talk to your research mentor, even if it's a professor, perhaps especially if it's a professor, to figure out what these things are, to figure out how success will be measured for you, to figure out what your deadlines are. If you don't know this information, that's fine. But if you learn it, you will probably have an easier time navigating your semester. Meanwhile, if you're one of the current graduate students, I hope this guide can help you decide not just which projects are excellent for undergraduate students in general, but also when your project might be ideal for an undergraduate researcher. Not all your projects are at all stages, and that's okay. If you feel like you're waking up in the morning and you just want to work with an undergrad, use that as motivation to get your project a little further along, to sort of build out, ask yourself, like, what are the 4 things here? What is this mature? How would I measure success? What are the prerequisites? What is this semester-sized project? And use that to motivate yourself to get to a point where you can get your undergraduate help. Ideally before you start soliciting for undergraduate researchers, which, let me tell you, is a lesson that we tend to all learn too late. So my apologies to anyone in the room who's had a first research assistant experience. All right, let's go back to our syllabus. I've just prattled on for like a solid 20 minutes about how to select a final project for your work. But I said syllabus in class, right? There's other things here beyond just that final project. Now we need to go fill in the rest, everything that leads up to our final project part of the semester. In particular, we should talk about how it starts. Where are we going to start? Well, you start wherever the students are. If a student comes to you doing research, they've got some background, and that is where you start your syllabus. And where do you want to get? Where the project is. You've done all this work to identify prerequisites. This gives you the skeleton of your curriculum. Your job now is to find a pathway that can bridge the gap from where the students come to you to where the students start. Your job is also to accept that there's going to be something there, that there will be some more onboarding than just read this specific draft of this specific paper. Let's look at some examples. So, in the project I did with Fearless Concurrency at Berkeley the first time, my student came in with a great degree of mathematical maturity. Where did my student need to get? Proving progress and preservation. Now, a great degree of mathematical maturity is excellent, but my student also didn't come in with any programming languages knowledge, or really computer science knowledge. My student was a math major. So what's the pathway that takes us from mathematical maturity to proving progress and preservation? Well, it's about a semester and a half of programming languages courses. This is a big lift. And I honestly thought that the student probably would just leave and not be able to do it. But rather than just say, I'm sorry you don't have the background, I took my time, I sat back, and I figured out how to create sort of week by week chunks of excerpts from types and programming languages that would teach what you needed to know to even understand that progress and preservation was something worth proving. And this took me a few hours, not super long. I mean, Benjamin Pierce is a brilliant writer and he does great course design. So I sent this over to the student and I was like, hey, this is probably too much. Here's the amount of work that would need to happen before you can start. And that student said, okay. And then 2 weeks later, that student came back and said, I'm done. And I said, okay. And we were able to get started. And that was truly shocking. And I say it not because you should only work with those students, but as an example that even if a student seems like they're a little bit far from what you need them to be, it's sometimes worth it to give them that chance to catch up. Okay, let's look at another example. This one is a pretty cool onboarding story. When I was working on Python when I was an undergraduate with Joe and Triram. Joe and Triram were also slated to be the professor and TA for the standard undergraduate programming languages course that fall. So what they cleverly decided to do was integrate all of the prerequisite knowledge that someone who just had like, I can program in Python and I've heard of data structures before, would need to go from there to I'm writing a core semantics. And they sprinkled it throughout the semester. They built literal classes and literal class projects around it. The final project of this class was the onboarding project for the research. We were supposed to take everything we learned about how to write operational semantics and then define an operational semantics and an interpreter for a language that looked suspiciously like a core Python. Which of course dovetails really nicely into a research project that is a formal semantics for Python 3. The real secret sauce connection that made this possible was the existence of PLT Redux, which is a brilliant tool that allows you to write semantics in an interpretery way, and more importantly, run your semantics against tests later. Okay, well, building things into a core class is a pretty out of reach thing for most of us, but you can do this sort of build a class mentality in general. Here's the third example. This is in distributed systems, so consequently I will say nothing about the research. This distributed systems project, we decided to advertise for undergraduate researchers one semester, and we wound up getting 40 interested undergraduate research assistants, all of whom had about the same combination of classes and previous experiences. It turns out that 40 undergraduate research assistants is too many undergraduate research assistants for, I would assume, anyone. But rather than tell them, no, I'm sorry, this doesn't work out, we decided to just kind of onboard them all. We sat down, we figured out what you need to do to get from the end of a class in our standard curriculum to the beginning of this project. And we built out, a couple of lectures and a couple of deadlines and basically ran an actual course on the margins of our semester in order to take these students to preparedness. We figured that beyond just teaching them the skills they need for the project, it'll show them the specifics of we're going to use RDMA and C++ style things and let them decide for themselves whether that was well beyond the pale or not. After this semester of the literal class, 15 wound up continuing on to do research with us, which, pro tip, is still too many. But there were 4 graduate students involved in the project. So we each took on about 3 to 4. They worked in teams. That was how we ran the semester anyway, and it worked out for us. So what do I want you to take away from these examples? I don't want you to see these examples and walk away from this thinking, my God, I'll never manage that. It's so much work. I have to write an entire course curriculum to work with one undergraduate. And similarly, as an undergrad, I don't want you to walk away thinking, I don't want to start research after I have to take an entire course. I want to start research today. These examples were very much outliers. Rather, the takeaways that I'm hoping we get out is that if you're an undergraduate, it's completely okay to see a research project that might excite you or might entice you and realize that you're not quite ready for it, that there's something more that you have to learn before you can really get started. that you open up a file and you see a squiggly little symbol and you're like, well, that's not good. The important thing, rather, is to be honest about your preparation and to be honest about your motivation. Tell your research mentor, I don't recognize these symbols, but I love this problem. And avoid the common pitfalls of either the fake it till you make it, of course I've done category theory, just assuming you can pick it up in the margins. Or on the other side, the fail early, fail often mentality of, I don't recognize one of these 370 pages, so I will not do this research. Let it be your research mentor's job to figure out if there is a good pathway for you from where you are to the research start that makes sense for the project. Don't ever say no to yourself. Meanwhile, other hat, if you're a project mentor, if you're a graduate student looking to work with undergraduates, just remember that the students who are joining your projects are not you. They will not have exactly your background. They especially will not have the background that you pretend to remember that you had when you think you're about their age. And they won't necessarily have a clear picture even of what their background is. They won't know whether they're good or bad at something so much as whether their class was easy or hard when they were taught it. And that's okay. If you have the time in your semester to put in the work to figure out what they're bringing to the table, what you need, and sort of build out that pathway between the two, even if it means building out homeworks or picking a textbook to select from, then you can get really rewarding experiences even with undergraduates that seemed initially ill-prepared. Conversely, if you just say yes and you don't do any of this, you're really setting yourself up for an undergraduate that ghosts you. Someone who's not ready for the research and doesn't know how to get ready for the research kind of definitionally can't do it. Okay. Let's return to that metaphor that we were using to drive the whole thing. The metaphor of a syllabus or a class for research. We've seen a final project, and we've talked about how to pick it based on our mature research. We've talked about the established prerequisites and how that we can use those plus knowledge of where our students come from to sort of bootstrap a pathway that takes our students from where they are to where they need to be. Now let's see how we can take advantage of how the fact that our project was easily divided into deadlines can mean that our semester keeps motivation up. Now, in the metaphor of the syllabus, when you have a final project and it's divided into deadlines, it's usually not the case that you are doing your classes and you're doing your homework and you're doing classes and you're doing your homework and then there's a sudden discontinuity where everything stops. And now every week you have a final project due and there's nothing else. I mean, maybe if it's like the last 2 weeks of term, that'll happen, but if it's a month or 2 month long project, that's really not how we structure it. Rather, we interleave it. The first deliverable or two of the final project will happen sometimes during homeworks, at the very least while lectures are still going on. What that suggests to me is that we should take the same approach we took to the semester's final project to each of these individual sub-projects. We should take each individual sub-deadline and ask ourselves, what's the objective here? How do I measure success here? What are the prerequisites here? Which will allow us to intersperse the work on our actual research with the work on the sort of learning how to do the research, with the prerequisite work. This is essential for maintaining motivation. No matter how motivated a student is, telling them they have 3 months of textbook work to do before they're allowed to talk to you is a real blow. Telling them they have 2 weeks of it before they can start reading your papers, and then another week or two before they can start building an implementation is way easier. I kind of said this, but basically, you want a gradual transition from the onboarding to project, because your project, which is enabled by your project being made from small deliverables. Okay. Good goal. Let's see it in action again. So what were the small deliverables that we could interleave for the Fearless Concurrency project? Well, step number 1 on proving progress and preservation for a type system. Read the type system. And you really should break it out at this fine granularity, because step 2 isn't write progress and preservation. Step 2 is understand. So what I did with this is I had my student go through my rules portion at a time and explain those rules back to me, what they were there for, what they were in service of. Things like, this is just the normal rule for looking up a variable in a context, or things like, There's a context split here because we don't want to accidentally reuse the same bindings on the argument side and on the function lookup side of this application. This is important not just for the purpose of teaching the student, this is sort of also part of the onboarding, but also for the rules themselves. Because as the student presented a kind of overcomplicated or missing the point explanation, sometimes it meant that, well, that was an overcomplicated or missing the point rule. So we could use this interactive process to refine the rules down to a simpler core that still captured what we needed them to capture. Once both their students' understanding of the project and the rules themselves are stabilized, time to formalize some invariants, some things that make the context sane, the actual shape the heap needs to be if the heap is going to support data race freedom. Now, I actually did this part ahead of time because otherwise I wouldn't have any idea how to structure the proofs. But I didn't show that to my student. I still asked my student to dream up invariants on their own, sort of as a sanity check, since I didn't have the proofs. If the student wound up with different invariants from me, that could be an indication that my invariants weren't going to work. Conversely, if the student had the same invariants from me, that's great. It's a strong indication that probably this is actually what makes the system work out. In this case, my student had the same invariants. Good. After that, we're off to the races. Each individual lemma can be its own subgoal. Eventually, you'll get to full proofs. Lots and lots of small deadlines just for prove, progress, and preservation as one task. Okay, when I was an undergraduate, what were the subgoals for the Python semantics just defined semantics? This one was also done very cleverly. Rather than have just surface Python, core Python, semantics, translation, we defined a lot of intermediate languages. And each time we defined a single intermediate language, we had to ask ourselves, what's the semantics of this particular intermediate language? Do we believe that this is just a desugaring from the language above? I know we eliminated arrays and replaced it with dictionaries in the sky, but did we miss something crucial that should have been preserved in the core calculus? As we assessed whether those were simple or correct, that would wind up, sometimes we'd fail. Sometimes actually that wasn't really simple or that wasn't really correct, and we have to rethink our rules or rethink the way we built our intermediate language. Once we're pretty convinced of that, we have to implement it, build out a desugarer, and then we have to run tests. Because if our desugarer was wrong, then that probably means our intermediate language was wrong, which means we have to go back to coding the rules and do that in a loop for a while. And there were 6 undergraduate students on this project. 3 undergraduate students and 3 other. I think a couple were like senior programmers at a company. I'm sorry, I was an undergraduate a long time ago. So there were but the point is there was a lot of manpower on this task. But eventually we'd converge. We finally got low enough that we still looked like recognizable Python, but we had simple semantic rules for it. And going any lower seemed like it would really eliminate something critical to being Python. So we had our full semantics and we were ready to test it and publish it. Okay, one last example. The Derasure project, the distributed systems project, how do we break that into deadlines? Well, the project was to build a memory allocator for a distributed system. So first off, rather than have the students jump directly into like a 100,000 line C++ 2014/17 code base, which I don't know if you guys sound really excited about that, but I wasn't. We built them out a private little space where they could build and test their designs for allocators and make sure that they were performant and correct without sort of dealing with the crazy build toolchain. After we managed to do that, we didn't go and integrate it. We wrote documentation about it. We explained the design of these individual allocator as though that was the whole project, talked about it with the rest of the team, talked to the other graduate students, and only then integrated it into the main system, the first time we touched the main code base. So what am I trying to teach with these examples? If you're an undergraduate, it means asking for deadlines at whatever rate you need to be successful. It means if you see something that seems like too big a lift, then maybe it is, and that's fine. It means talking to your graduate student when that happens, or talking to your professor when that happens, and trying to get that broken down, not just assuming if you can't see the next step, clearly it's your problem. Meanwhile, for graduate students, it means basically exactly the same thing. you should really know what it is your undergraduates are working on. And I don't just mean they're working on the Python interpreter. I mean, they're implementing desugaring phase 2.c, and the hard part will be this. You should know how they should break that down. What is a task they could do in the next 4 hours? And if you don't know that, and if you can't figure it out while sitting down and thinking hard about it, you know more about your project than they do. So that certainly means that they're getting set up for being stuck. That is a time to call your undergraduate student right now and be like, hey, let's set a meeting. Let's figure out how to divide this goal. Now, sometimes you'll work with undergraduate students who are distinctly smarter than you. I've definitely done that before. So it's totally possible that you'll have that meeting and the undergrad will be like, yeah, obviously the correct way to do this is to points to vague adjunction on the board to a category you've never heard of. And you'll be like, awesome, those were words. And, and you can let them run, that's totally fine, but generally don't assume they know more than you. Sometimes they do, let it be a nice surprise. Okay, that's enough examples for this one. Let's return again to building this syllabus. We had a final project, we divided it into sub-deadlines, we interleaved those through the semester, while we also worked on an onboarding that was more extensive than just reading a paper, but consisted of teaching what you need to know to start a project. The last thing we're going to need to do is measure success. Now, I'm running short on time, so I will say this very briefly, but I want to return to the opening point, that the research experience with an undergraduate student, honestly, the research experience in general until like you're going on the faculty job market, is a teaching or learning experience. It is not about getting the research done or publishing the paper. It's about staying engaged. It's about making progress. It's about learning more about the problem. Okay, disclaimer done. I've set up all these projects. I should tell you how they turned out. So let's measure success for the fearless concurrency type system project. The first time. This is the one where I kind of just told someone to build an interpreter and didn't even know why that would be useful. Surprising no one, this project didn't really have a good way to measure success and didn't succeed. And that's because as the research drifted further and further from the project I had assigned, I could spend less and less time explaining to my student why they might do something. I couldn't anticipate problems they'd run into because they were working on a completely different artifact by the end. Ultimately, that left the student adrift, with no research goal to motivate them and with no research mentor to create sub-deadlines for them. They just kind of disappeared throughout the semester. I wish I hadn't done it, and I'm sorry to that student. But, you know, cautionary tales. It went better at Berkeley. This project, luckily enough, worked exactly as expected. Our deadlines came in rapidly. The students stayed incredibly motivated and engaged. We got really lucky in that the invariants that we wrote matched, and the proofs and lemmas that I set up at the beginning were roughly what you should have proven for our results to hold. It wasn't just like turn a crank and it all goes through. There was serious creativity, and indeed my student found some bugs in the system that required us to redesign a couple of rules. But ultimately, it did fit in the semester I had hoped. And that student has gone on to do a lot of successful research as a grad student, PhD student today. Meanwhile, when I was an undergrad for the Python semantics, was this project successful? Sort of. We published the paper, so I would say also a success. But it was a much rougher one. It turns out that saying, design is semantics, kids, to a bunch of 19-year-olds who had never done programming languages before, will get you some really weird semantics. We didn't exactly have the equipment we needed to make the value judgments about whether each step of desugaring made sense. But we stayed motivated, we stayed engaged. We always knew what the next step was. And because our graduate students stayed on top of us, because they knew what we should be working on, weird things like, hey guys, you just completely desugared away Python scoping issues, were caught early, and were caught often. And it allowed us to really actually have a successful project, even though we were a little bit meandering in the woods for some of it. Ultimately, did the students go on to have success? I mean, I became a professor. The other undergraduate student is I think, lecturer at Northeastern now, and the third undergraduate student is a PhD student. So I'm going to call that a successful research project for the students. Also, the weird curveballs we kept throwing turned out to make the research way more publishable. Python scope is really messed up. Meanwhile, Duratio. This is an example of a project that didn't work for the research, but did work for the students. I designed a complex allocator that I thought would work really well for our distributed domain, and it didn't. And it didn't for reasons that were surprising, assumptions that we thought we could make about the hardware that turned out not to hold. But the students stayed on top of it. The students built out the design basically to spec. The students innovated, found ways around our problems, pointed out when we actually hit a fundamental error that we hit a fundamental error. So, successful research project. What's the takeaway lesson here? Success is not about publishing. Success is about engagement. Success is about learning. Success is about discovering something in your research. If you are an engaged undergraduate student that keeps surprising your research mentor and doesn't publish a paper, you're getting an excellent rec letter out of that. And that's going to matter more for getting into grad school anyway. Okay, well, I'm over time, so I think it's time to wrap up. Let's just say, ooh, someone said something.
No, go ahead, wrap up.
Okay. Let's just say that this metaphor is only a metaphor. And I want to return to my first point, which is that no plan will survive first contact with your research students. Everything changes all the time. There will be a bug and it's critical, and suddenly your project is no longer implement the interpreter, it's go back and rethink the semantics. The point of thinking about this, the point of building out this plan, thinking about prerequisites, interleaving small deadlines, is not to create a contract. It's about the planning. It's about making sure that you have a good answer for what a research project is, because that's the recipe for success when working with especially early stage researchers. Just be flexible. And now I'll take questions.
Time for a question or two.
Hi, May, great talk, thank you.
Thank you.
I wanted to ask, in terms of measuring success.
Sure.
Because one of the things that no matter how mature the research project is, it's still a research project. So there is the possibility that it crumbles into dust while the undergrad is trying to get a project out of this.
Right.
How do you then lead them into success and measure the work that they've done when their foundation has gone?
So there's sort of two options here. One is it crumbles into dust and the student's work is instrumental in crumbling it. That's great. That is success. You've just measured it. Congratulations, student. You get an A+. Also, I'm sad. There's the other sadder option, which is your student is working on an example of a type theory and you prove it's unsound 2 weeks in. And now there's clearly no point in that student continuing with that example. Honestly, change the project. Go back, say, hey, we've learned a lot here. You've built some skills on how to build out type theory, but we can no longer use this example because we no longer have it. And if you don't have anything else to do research with for that semester, find a way to do right by that student, even if it means converting to a more class-like, here, instead of doing research on my system, we'll do a system that's more stable, a system that's been published that we know is sound, and build examples there. And ideally, you'll have a project that's a little further on and doesn't crumble. You can get really unlucky and just every 2 weeks your system crumbles, but at that point, you've got probably many concerns that are different than your undergraduate's research success. But yeah, I guess flight to stability tends to be my reaction there.
Thank you. That was very interesting to hear your perspective on both as mentee and mentor in these projects. I did have a question, which was, I've had some experience with doing tutorial teaching, class teaching, where, at least in the system I'm from, you have the distinct advantage that your only purpose is to help the student learn. You have no role in the assessment of the student. It seems with research projects, kind of inherently, you will have to be involved in some way with assessing the outcome of that, even if nominally there are independent assessors, your kind of report will form part of that. How do you kind of balance the kind of joint obligations to making sure they're learning, but also having an assessor hat on at the same time?
I don't have an assessor hat, is the short answer. My primary way of measuring success on research is measuring engagement. It's already so hard to make progress on these things that a failed student, in my experience, is a student who just kind of vanishes over the course of the semester. And that a student who sticks with it and demonstrates success and gets to the end of the semester having learned something useful about research, getting distinctly from where they were at the beginning to where they are now, even if it was not successful in your project at all. I tend to see that as kind of an A student. I'm also from America, the land of great inflation. So it's fairly usual for like us to take undergraduate research assistants and just kind of slap A's on 2/3 of them. We could go deep into debates about what the point of grades are and whether this is a like moral and ethical philosophy or not, but I get to use that to avoid these deep assessment questions when I work with these undergraduate students. And that's been very good for me. The other short and pithy answer is if you're a grad student, which I think most people in the audience are, you have a professor you're working for whose job it is to do that for you. Just make sure you're communicating with that professor enough so that they have the information to make that decision.
All right, let's thank May again. All right, so we have come to, I guess, the end of our formal PLMW program. So we just wanted to thank a few people. First, we want to thank our amazing student volunteers who have been running around with the mic. There are multiple sitting behind you in that really fancy control room and making sure everything works. So let's give them all a round of applause. We also want to thank all of our panelists, all of our speakers. We're going to focus on May because you're right here, for taking time out of their busy schedules to put together these lovely talks and be here and answer questions and hang out at lunch. So give them all, I know there are others in the audience, a big round of applause. We want to go ahead and thank all of our sponsors, which are conveniently nicely on this screen up here. So we do have a sponsor, Jane Street, that is doing an event this evening. So in a second, I'll call Chris up to give some instructions so I don't accidentally get you lost in London. But first, sort of one bookkeeping announcement. You will be getting a survey by email about PLMW, about your experiences, about the sessions, what you liked, what you didn't like. We actually use it to inform how we plan future PLMWs. Please fill it out. And if you don't fill it out, you won't get reimbursed. So hopefully that's enough of you've got the carrot. Please fill it out to like help us improve PLMW, and also the stick, which is you probably want money. Okay. So Chris, take it away.
Yep, so Jane Street is hosting a board game night tonight, to which you are all invited. Please come. We've ordered a lot of food. It's going to go to waste if you don't come. If you're a graduate student, you should know that's bad. The easiest way to get to the board game night, which is at Jane Street's office from here, is to take the Circle line from Temple to Liverpool Street. This involves riding the tube. Riding the tube is easy. You just like tap a credit card on the way in, tap a credit card on the way out. It's less than $3. Should be easy. I am going to walk from here to the tube station now. You are welcome to follow me.
Yes, the address is sort of if you click on the event on the POPL schedule, it is there. Yeah. So I think we're going to, I guess, congregate in the next 5-ish minutes right outside this building to start making our way. All right. Thank you, everyone.